Good afternoon, all the delegates, the speakers, and the online participants. It's an immense pleasure that from the Lovraj Kumar Memorial Trust, we are conducting a webinar on energy storage. Specifically, we are looking at battery and hydrogen in this session. And we have divided the webinar in two parts. One part is the technical session, where there will be 5 speakers. Followed by that, there will be a panel discussion on a similar topic or a topic of a similar nature. And then finally, we will have a conclusion session by Dr. R.K. Malhotra. First of all, we really thank all the speakers to agree to be there in today's program. They're very busy and they're expert in their own field, which we will be talking about. To give you really the positioning ourselves for today's deliberation, in last 1 year, the world has added 5 gigawatt of energy storage from 2000. I would say, I won't say that last to last year, from 2019 to 2020. So currently, storage means is across the meter. That means the electrical meter. So currently the 17 gigawatt, not gigawatt hour, gigawatt of storage across the utility or across the meter is being used throughout the world. The bulk of the share comes from China and US, 1.6 gigawatt and 1.5 gigawatt. European Union was 0.8, South Korea 0.7, Japan 0.4 gigawatt, and the rest of the world is 0.2 gigawatt. So India, of course, has a huge potential because India is generating a huge amount of renewable energy. It is currently about 20 gigawatt or 30 gigawatt to, it will go to 50 to about 120 gigawatt from by 2030. So about 120 gigawatt of energy storage, I'm talking about the energy storage, is the requirement in India by 2030, and about 50 gigawatt in 2025. So looking at this, there's a huge potential of development of energy storage platform in electrical energy for the utility service. Followed by that, I would also like to highlight that e-mobility is very strongly coming up in India. And obviously the e-mobility hinges mostly on the storage of energy in battery, more so in the lithium-ion battery. I must confess that out of all the storages that I talked about, more or less 17 gigawatt across the meter, the 93% of the storage is coming from lithium-ion battery, and the rest of the types of batteries is just only 7%. So right now we are looking at lithium-ion battery as the main source or main storage medium, and rest is, as I said, but there is a huge opportunity in the other type of batteries like sodium-ion batteries, supercapacitors for e-mobility, even in certain cases in industry or in utility service, and redox flow battery, and then hydrogen and fuel cells. So hydrogen and fuel cell, the hydrogen storage we are going to talk about today. We are not talking about the conversion devices, only the storage. So we will talk about the hydrogen storage, of course, and that has a huge potential as well, both for the mobility as well as the electrical power. So with this introduction of today's webinar, and good that all these oil company or energy sector companies have to shift their business towards the renewable energy and storage in coming 20-30 years. And with the decarbonization is getting important, and that we took a our Honorable Prime Minister has already mentioned that by 2070, the India will be totally decarbonized, and world want to decarbonize by 2050. Then these are the way to move forward. And the refinery will be, tomorrow's refinery will be different from what we see today, mostly based on the biorefining, and the petrochemicals will come from biomass rather than fossil fuel. With this introduction, I would now hand over I would start today's the meeting from the trustee side, Shri B.K. Chaturvedi, who's a former cabinet secretary of Government of India and the chairman of Lovraj Kumar Memorial Trust. He will give his remarks, and followed by Dr. Deshpande will introduce the speaker, and then it goes on. Thank you.
Well, thank you, Professor Basu. I have a slightly bad throat, so please bear with me during the couple of minutes that I will speak on. First of all, let me thank all the speakers who have accepted our invitation. We are very grateful that because of them, the webinar would really help us in understanding the new technologies. As Professor Basu mentioned, and in the earlier discussions informally when we were talking, the major issue today is the question of energy storage, and this has become critical because the various climate change issues require that India and the world goes on to this 1.5 degree increase Celsius of our targets. This is getting increasingly difficult now, even though India is well on its way to moving its target as we accepted in the Paris conference. But there are many countries which are slipping up, and it has become very difficult. Now, even in this situation, as India moves forward, we have a large number of cities which have a very high level of pollution. Some of the polluted cities in the country and in the world are from India when you find out the classification. So it is important, therefore, that our major source of pollutant, which is the transport sector, that goes on to the cleaner vehicles, in that context, the role of battery has become exceedingly important. I recall way back when I was discussing the US those days, the problem of batteries. It was well accepted that battery is the key on which the whole thing hinges, and battery technologies development is important. Many speakers will give their views, and Professor Basu talked of lithium-ion batteries, but I look at it also from this perspective that in the Atmanirbhar Bharat, one should also have a look at not only the technologies, but what are the raw materials available in our country by which we can produce some of these batteries for our use. That will be another perspective. I'm sure that when the panelists discuss this question, that will also be kept in mind. The question of hydrogen storage, Professor Basu mentioned, it is a ticklish task given the nature of hydrogen and its large volumes. So far the methods used have had marginal success. I think it is an area we need to work on more now, so that it is so far doesn't remain only in the context of demonstration and experimental stage, but goes on to commercial work where hydrogen can be used, because hydrogen is one, in case it can be used and it can be stored effectively, then it can give us very, very clean energy, and there would be very little emission. I'm sure that today's deliberations could be exceedingly useful and we will find the discussions will be taking forward the process of development of the technologies in the field of battery and energy storage. From Lovraj Kumar Memorial Trust, I extend once again a very warm welcome to all the speakers and look forward to listening to their views. Thank you very much.
Thank you, Mr. Chaturvedi. Professor Basu and our chairman, Mr. Chaturvedi, they have already laid out the right kind of framework for the commencement of the webinar, and we have a series of experts in their own field who have been lined up to give their presentations on this theme. First of all, let me give a warm welcome to all the delegates who have joined for today's webinar. We have had a strong presence of delegates in all the earlier webinars that we have had. This is the fourth in the series that we have had, the first two being on oil to chemicals, the third one being on carbon capture and utilization, and this fourth one, a logical step now towards battery and hydrogen storages, because that's what whole world is talking about. So let me begin the webinar today through a formal introduction of this speaker one by one as they come. I'll begin with the introduction of Professor Sampath, who is going to accompany me and join me in coordinating this session. He will be taking care of the question and answers part after each presentation. Professor Sampath is an electrochemist and a nanotechnologist by specialization and is professor in chemistry at the Indian Institute of Science, Bangalore. He is known for his studies on supercapacitors and nanobiomechanics, and is also involved in research on the interfacial properties of metals and surfaces. He is an electric fellow of the Indian Academy of Sciences and the Indian National Science Academy. The CSIR has conferred on him the Shanti Swarup Bhatnagar Prize for Science and Technology, which is the highest Indian Sciences Award, in 2006 for chemical sciences. He has reviewed several peer-reviewed articles to his credit, and we welcome Professor Sampath for the webinar today and having given his contribution as a member of the technical committee for the webinar. I'll also introduce the first speaker today, who will immediately take over after the introduction of the speakers. Dr. Ilangovan, he is a PhD in battery electrochemistry from the Institute of Science, Bangalore. He is going to speak today on lithium-ion battery. He is now with the Vikram Sarabhai Space Center under ISRO, and has worked on areas like design, technology development, qualification, production, and supply to launch vehicles and spacecrafts. The areas that he has worked on are energy storage systems, insulation systems, thermal protection systems, propellants, special polymers, ceramics, analytical area, etc. His areas of interest are nanoscience and technology for materials and energy systems, and attaining self-reliance in energy storage needs for the country. He has had extensive publications, about 30 technical publications and 3 patents. He's a member of several technical committees of ISRO, CSIR, MAITI, MNRE, DRDO, etc. Has done several technical presentations in international and national conferences, and membership of several professional bodies like MRSI, SSI, SPSI, etc. He has been given a gold medal for the year 2005 by the Astronautical Society of India for meritorious contribution to space technology development program. I have great pleasure in welcoming you, Dr. Ilangovan, to give the first presentation today on lithium-ion battery.
Yeah, very good afternoon, sir. Thank you so much for the nice introduction, and very good afternoon to all the participants, as well as especially let me thank the Lovraj Memorial Trust for giving me this opportunity, and thanks to Professor Sampath also, who led the LKMT to me. So thank you. Let me go ahead with the, I think, sharing the screen.
You have 20 minutes, Dr. Ilangovan.
Thank you, sir. I will try to complete within that time. I hope my screen is visible.
Yes, it is.
So hope, sir, title of my today's topic is lithium-ion battery for me, but I have also slightly sneaked into our Professor Tata Rao's area of supercapacitor also. I will take about 1 or 2 slides with respect to supercapacitor, because why I have made this as a super battery. I will just tell you when I come to the point actually. So let me start with that, my fond tributes to my guide who was in Indian Institute of Science way back in 1985 to 92. Without whose guidance, I wouldn't have come to this level. And thanks and fond tributes to him. So overview, as we are the topic of the day, energy storage, and how the energy storage is relevant for electric vehicles, and how the batteries as well as supercapacitor combination will work. And what are the small gaps that we have, and how we will be able to achieve sustainability aspects and technology development. Some of these things, I think the cartoon will speak. What is the role of energy systems, how costly when compared to the other systems when it comes to electric vehicles. So we know, all of us know that the energy cognition started from a fire to group of people to animals to then kind of machineries were coming up. So the per capita energy level was going up, and not with a very welcome way. In addition to air pollution, global warming kind of aspects were there. But definitely 21st century, we will have to depend on energy need for several of our application day-to-day life. So though 20th century was fully about founding on the wealth creation based on fossil fuels. So if that is the case, as it was pointed out by other speakers, it is the carbon dioxide and the areas, the stakeholders for generating the carbon dioxide are all given completely here. The areas, agriculture, residential, industry, electricity, and transportation, plus each country has given the quota of carbon dioxide, and the carbon was the issue with respect to today's our problems. And transport, definitely all these aspects we will not be in a position to avoid, but for finding out the solution. Yes, now look at the energy consumption, and which is completely in line with the population increase. So that's what the curve here. Let me try to get the pointer. So okay, so the energy curve actually it is well in line with population. So we will not be in a position to control the population growth, but growth rate we can try to control. So in that connection, energy and population will go hand in hand. So without carbon emission is the agenda before us. So what is that we are planning to do is that we'll have the globe, and we'll have the goal to see that the carbon dioxide is coming up and the green aspect is maintained. The only way alternative, as all of us pointed out, is that the God-given, the nature's creation of solar is there when compared to all other energy sources. The sustained energy is coming from solar, sun, that is about 23,000 terawatt at an instant of time. So any increase in the population and the increase in energy, if we are completely making it dependent on renewable basis, definitely the carbon emission as well as the related effects can be overcome. So when it goes to sun, means sun is not available all through the day 24 hours. So we know it is intermittent. And whenever we are not using the power, much sunlight is available. Whenever we need, sunlight is not available. So the energy storage becomes definitely a relevant portion today. So in that perspective, there are many types of energy storage technologies available. But is it possible for us to adopt all of them? When it comes to especially mobility, if you see the capacity for energy, but the time duration it is available is very short. So when it comes to especially mobility, it is the electric based systems like battery is the one which is very important, because I cannot carry for a mobile or a car or my even for our launch vehicles what we are working on, I cannot carry kind of magnetic storage or the flywheels or long duration compressed air kind of things is not possible. So it becomes confined to touch of a button, I am getting the electricity. So when it comes to that, mechanical aspects will not be sustaining it, and rechargeable aspect, if you have to sustain it, becomes the battery, and which is the versatile form of electricity. We know the space people, yes, our requirement is very less, but still it is launch vehicles, spacecraft, there are different types of functions which I don't want to elaborate here. But Still, the technology-wise, we have no other go but to develop electrical energy storage-based energy systems, where these are all the parameters which are depending on, which are very much relevant for our terrestrial applications also. If that is the case, what are the systems that we will look at? It is that batteries, several batteries are there, supercapacitor is there, even RTG is there. So these are all the systems. Throughout the years, decades, we are getting the power systems where mass is coming down, energy density is going up. So now that for terrestrial applications, again, all these points of the technology management, like raw materials, process engineering, infrastructure, indigenous development, and this last point of institute industry participation, I will try to throw some light on that. So all these things will be relevant, but there are some more points which are relevant if we have to make it sustainable, as well as carbon-free conditions we'll have to reach, means cost should be less, sustainability is a factor. And what is the role of a government? In this portion, I need not explain, it becomes indefinitely evident. So coming to lithium-ion system, today's our topic when I come to, it's a simple system as far as today's knowledge of advancements are concerned. The anode, without talking anode and cathode, it will not be complete. So I will not be dwelling into, because the colleagues who are participating or distinguished guests who are there may not understand the chemistry portion. Don't worry about it. There are two terminals in any battery, one which gives out electron, which is coming over here. The electron is coming out from one area, and another area it is getting consumed. What may I take? Fine. So the main aspect is that there are two materials in one cathode and anode. If you see this equation, if I look at it, actually the red one, which is the lithium, is taken from one material and lithium is actually loaded into another material. In the process, the electron comes out and gets in. So that side, okay, gives the complicated mechanism for the several of the people, and the charge and discharge. That means the energy is available as a voltage from the lithium-ion system, and wherein the lithium is moving from one electrode to another electrode inside the cell. So electron is in the outside and the lithium ion is inside. That's why we call it as a lithium ion. Because of the movement of the lithium ion from one electrode to other electrode during charge and the reverse process of discharge, it is called as a rocking chair. The lithium is rocking between two materials. So this is what is the essence. If that is so, what is so difficult? Why the problems are there? If you look at it, yes, process technology is available for us. We start with some chemicals. There are some few set of particles are there to become battery, give life for that. So that's how these kind of systems are there. If we start with some of these materials are available at the left side, we have a kind of the solution, and which is becoming a slurry. The slurry is coated onto some of the materials like aluminium, copper, and then we get the slurry rolled, and the slurry becomes the electrode. And the electrode, we are taking it for different type of equipments, and then equipments will roll the stack. So these are all little bit of like technical aspects, which I don't want to dwell much into that. So these powder particles are becoming kind of a roll, and the rolls are actually bound to give the stack, and this is the stack which is used. What I'm trying to say is that I'm just giving a grip about the system, starting from particles. These are all the hardware elements, some precision slurry coating materials, technology is required, infrastructure is required, and several type of industries are required to support, and the raw material supply chain. All these aspects are important, which we have mastered. Yes, mastering, we are now getting the cell that is coming out of the technology and the lab, or it's an industry. But what is the problem? Infrastructure, yes, different type of infrastructure is also available. In slurry, in a summary, if I look at it, the baseline technology to produce the lithium ion is available. Fine. Then why we have this kind of hue and cry? But this baseline availability also well demonstrated by my hard work of my colleagues. We have started from 4 ampere hour to 100 ampere hour for satellites. We have demonstrated, ISRO has demonstrated, VSC colleagues have put in their life and efforts, a lot of efforts have gone in. But still, there are some issues with respect to making it more and more efficient, means automatically making it cost effective, making the technology affordable, making the technology reliable, safety, eco-friendly. There are some more points which I love. So here, if I look at, this is the energy curve, this Always we have this graph. Left side is power, right, the bottom, the right side, the x-axis becomes the energy. So energy, if I look at it, if I see the 100 lithium ion is somewhere around 200 watt-hour per kilogram, it is available. And at the same time, if I look at the supercapacitor, I will just refer it, I will not dwell into that. I have enough power, but energy level is very low. But I have energy here, but the power level is very low. This is what is the issue today, which we are talking about. Electrochemical systems are in the pinnacle. You see the fuel cell, you see the capacitor, or any other systems. If we have the energy, that means at a level, it can supply, it will be supplying for an hour or 2 hours, something like that. But when it comes to peak power, see, electric vehicles, always we have kind of wherever the requirement of the gear change is there, I love to ramp up, I love to cruise. That conditions, I need a little more power also during this, like upslope is there. I need the power also. So that means I need the power, which is the left side dot. I need the energy, which is in the right side dot. But there is a small gap actually, not only small, it's a big gap. But when it comes to internal combustion engine, where the electric vehicle is fully dependent on now, if you look at it, this is somewhere on the right top, where energy is also required, as well as power is also required. So this is the gap which I have to fill to make the system more and more efficient. And if I am doing so, in that process, if life comes down in the cycle life, then cost goes up. The reliability aspect, then safety aspect. These aspects, how I am going to overcome to make the existing system more and more efficient, or in future, like aluminum ion or sodium ion, even if any battery comes, the situation is more or less same. The energy is available, but the power is not available. Supercapacitor is one system where power is available, but energy is not available. So now, how to fill these two gaps? I will be more concentrating on lithium ion only. Supercapacitor, I will just bring in the intricacies of making the supercapacitor. Maybe probably our Dr. Nursing Rao may be the touching, because I don't want to get into that domain. So this gap, how we are going to fill it, how we are going to make it sustainable. Yes, first of materials are available. Is it enough that we are able to improve the energy density? Like now we are starting with carbon, that is somewhere here. If I am going to silicon, definitely I will be able to increase the energy density. Is it sufficient if I will be able to make a system? Host of materials are available, anode material, cathode material. But in spite of that, there are still some more limitations. Even if we go to lithium air or lithium sulfur, we are not in the position to meet as well as the harvest the full energy available from the battery for the adequate duration of maybe about 5 years or 10 years, or about some 5,000 cycles. If I get, then the cost will come down, as well as the charge aspect is coming into picture, discharge aspect is coming into picture. If that is the condition, I have to improve this aspect in spite of the system being available to us. See, what do we mean by that? Energy density goes up. If you look at this barrel where lithium metal was there, I'm increasing or actually concentrating the energy within the system. Mass level comes down, but the power is not going up. So that is what it means, that if I from 100 watt-hour per kilogram, if I'm going to 500 watt-hour per kilogram to the right end, I am only reducing the mass and increasing the energy density, but the power portion is still not at rest, which is killing the life of the battery or killing and increasing the cycle life, the cost portion of the battery. So increasing the energy density alone will not give our comfort portion. That's what now the red button has come to the right side, that I am able to touch the energy portion of the internal combustion engine. At the same time, there is a gap still between the supercapacitor power level I have to meet the internal combustion engine. So this is where if the battery is able to meet the power, but it is not in a position to meet. Why? Is there any issue? Because any energy storage system, it may be getting charged over maybe the daytime, but I need to get this power out during about 3 to 4 hours, but over 12 hours, whatever energy stored should come out in 3 to 4 hours. Means it will be storing the energy at a lower rate, but delivering the energy at a very high rate. So that's what is actually an efficient energy storage system. But batteries, if you look at it, rate of discharge brings down the energy. Low temperature brings down the energy. See, this curve, depending upon the different rate, actually the energy is coming down. start with 10-hour rate, I am having double the energy. But if I am going to the higher rate, wherever I need the peak power kind of conditions in the electric vehicle, the energy available is low. So if you see all these conditions, the voltage level, charge, fast charge rate, fast discharge rate, all these things are eating away the energy which is not available from the battery. Is it technically or conceptually meeting? Yes, it does. So that's why the available voltage is reduced by I times the resistance values, which is the negative form, and I is the one which is causing the heat to get generated. So if I force high power, automatically I will be losing the energy. That is what it conclusively says. Is it true? Yes. If I look at the kinetics, if I look at the electrode construction, if I look at the how the electron is coming out, all these things are definitely in line with why it is having a slow kinetics. Now, how I am going to come out of this? Energy is available, like it will slowly only give it. That is it possible that I am going in about some 30 km/h speed? Not possible. Supercapacitor, we know how this conventional capacitor and supercapacitor are differing. So I don't want to get into this one much. So, but still, I will use the concept we have developed. So one is something like the rabbit, where the charge and discharge will be fast, it will be coming down. But another one, the battery is something like a tortoise, where it will be slowly going, but for a long time. If suppose if I am able to mix these two, whether I will be able to get is the point. So we have done the development also here. So concepts are very much meeting. Cycle life is there. So safety aspect also there. In our launch vehicle, we could also prove the technology of supercapacitor. Everything fine. But only thing it will be able to give only for about 1 minute or 2 minutes. Where trams are all using the supercapacitor, but every minute they have to charge it. But this is the time at which we were able to concentrate on battery and supercapacitor. Suppose the one which is having a lower energy, but the higher energy, lower power. But electrochemical capacitor, higher power, lower energy. Suppose if I combine these two as a hybrid, I will be able to touch both the power aspect as well as the energy aspect. So that was the one which gives the confidence. See, if you see the blue curve, where at a slow rate we will be getting the power. At the red curve is the one which if I increase it by 10 times, I will not be able to get anything. If I combine the supercapacitor, two supercapacitor across one battery, I am able to get the 7.5 peak as well as 0.7 continuously, which is the ideal condition which is required for any electric vehicle. So now this was the confidence. We tried, we combined the concept of two concepts into single hybrid system. We could see the red line where we are able to get a very low drop. So the energy is fully available, power it is able to meet. Otherwise, the blue one which will be drawing so much. So any electric vehicle, suppose in line with battery, if I am having the supercapacitor also, definitely I will be able to meet. But the problem is that I have to carry two devices. And if I am carrying two devices, then the problem is that the efficiency comes down. Can I combine these two? That means if I take the battery electrodes, anode and cathode are there, capacitor, anode and cathode are there. If I combine the anode with the cathode of ELDC, I am again limited by the capacity of the supercapacitor on the right side. The cathode is limiting it. What is to be done? That is what was our the complete problem. So the peak should be handled by the supercapacitor, and the continuous sustained current should be handled by the battery. That's how we were planning. So when we planned like that, one small car with the Sharma being inside, we could demonstrate if both I am having, but the mass wise we are not able to. There are a lot of electronics comes into picture, taking care of the voltage of supercapacitor, taking care of voltage of the electric, the battery kind of things. So this was making us a little more uncomfortable. So what we did, we combined both the electrodes inside itself in a novel way, which I will tell you now. That is what we are calling it as supercapacitor. So each one becomes complementary in each other. So that way we were able to combine the concepts of both the electrodes. So that was acting as a very good power delivery, as well as the power delivery of supercapacitor, energy delivery of battery. So that's how we were able to do, and we could get the battery performance. Peak performance is coming, overcharge it is able to meet, safety conditions it is meeting, short circuit it is able to give even about 380 ampere. These are all tested values which we could deliver. So with that, we got full confidence about with respect to when I combine these two concepts of materials of supercapacitor as well as battery, I am getting supercapacitor That is what is the title. So battery is complemented for power by the supercapacitor, and supercapacitor is complemented for energy by the battery. So this was the concept which we are having it in mind. You see, complete, so many, even 60C rate, nearly about, if I say nearly the full capacity, I am able to deliver over 800 pulses per hour. So when compared to supercapacitor alone condition, I am getting continuously this many pulses. So this is the confidence which we demonstrated. And we could also see that in a nutshell, why supercapacitor. So like if I am going into downslope, all those things, there will be power, back EMF will be coming up. That back EMF we will be in a position to use it for the recuperation of the battery charge itself. That way, if you look at it, peak power is handled with supercapacitor. Peak backup also is saved with the supercapacitor. But at the same time, the battery is not allowed to see the peak current, so life is improved. So the safety aspects are also better, and the short circuit aspects are postponed. Thus, by cost aspect comes down. So these are all the points which we were looking at. So now, in like our management parlance, now earlier occasions the tortoise and the rabbit were alone, means they were having difficulty. So both of them were the lose-lose situation. So the rabbit and the tortoise were apart. But nowadays, what we do is we combine both of them. In land, the tortoise goes on the rabbit, and then when it is water, and the rabbit goes on the tortoise. So it is a finish line, both of them are reaching. So by combining these two concepts, we could get a situation wherein power as well as energy. So now that I am able to confidently say that supercapacitor and lithium ion, if we are able to combine, we will be definitely meeting the IC, internal combustion engine. So the supercapacitor is able to thrive the battery. So battery concept alone may not be sufficient. Even if I increase the energy density, there should be a capacitor in parallel. So that way we will be able to make them together a complementary system. So that's why we will be able to meet the requirements in a much better way. That is what is my point. So technology development, all our colleagues here, supercapacitors up to 500 farad we have gone. Supercapacitor wise up to 3 for our requirement. It can be easily scaled up. So this is yet another situation where we demonstrated to Honorable Minister in 2009 in Pune for a big car supercapacitor plus battery we could demonstrate. So with this, let me come to the summary. I have taken about 2-3 minutes more. Thank you for the time, sir. And it is the battery will deal with the high energy, but less power. Capacitor will deal with the high power, but low energy. The complementary system will be like supercapacitor, where the energy and power is combined, which reduces the size and mass of the battery, improves the runtime as well as battery life. So finally, what we are achieving is that efforts to improve should still continue, and it is the materials which will give us the way for storing the energy and deliver the power for the future. So then yet another point is that for when it comes to indigenous aspect, development of the technology and management of the technology means supply chain is fully dependent on the raw materials, and the raw materials should come from our own country. Now the process engineering is there, but materials are being imported, and the total infrastructure has to be developed, means it should be indigenous technology. So if that is so, both institute and industry should participate together and see that whatever the technical requirements with respect to materials as well as technology and engineering, if it is developed within the country, we will always be leading, not depending on some other country for obsolete technology. So with this, let me say that the cost effectiveness, affordability and sustainability aspects can be met with the eco-friendly aspect definitely. And for that, government should play a very good role to see that wherever the technology should be improved, wherever the funding should go for, and it is a focused effort should be there. Institute can come out with materials and process engineering. Industry shall be in a position to completely adopt from that, and definitely it is easy for us to prosper. So at this juncture, let me thank our Lovraj Kumar Memorial Trust charity trustees, the chairman, plus all the members. At that time, let me also thank my colleagues and management for giving me this permission to speak to you. And when we are eating the fruit, it is always good to remember the people who planted the tree. That's how the scientists and engineers who are part of the India side, whoever is there in the photograph, it is there. Thank you so much, and very, very best wishes. And thank you, sir.
Thank you very much, Dr. Ilangovan.
Thank you, sir.
I see that there are a couple of questions in the chat box. One of them is related to the cost reduction roadmap for supercapacitors. And I'll just read out the second question also, which possibly you can comment on, and that is related to the analytical methods by which materials and components can be ensured safe. The second one is related to the safety aspect.
So let me answer this one, or you are going for the second one?
Yes. I would like you to answer this question if possible. Yeah, that's right.
Sir, there are definitely analytical methods available because we do have our own facilities, and all over the country also these analytical methods are available with respect to raw material assessment and analysis, and with respect to cell level testing purposes also we have not only we have, and it can be easily established and is fully completely the power electronics and control systems. The technology is available, as well as there are centers which are doing, like in Pune, they are doing complete assessment of the batteries. Any battery that is meant for electric vehicle, it can be characterized. Sir, there are facilities available definitely.
The first question was related to the cost of supercapacitors, and where are we right now, and can you have a roadmap for cost reduction?
Sir, cost reduction wise, yes, you are right. Actually, VSSC has developed the supercapacitor technology, and our Kerala Electronics, Government of Kerala unit has taken the technology from us. They are now actually scaling it up. So cost effectiveness is definitely there. But if we can make the raw materials within our country, and that can be used for making the electrodes, the cost can still come down. Presently, it is imported raw material where the process engineering is ours, and we convert the electrodes as well as the hardware materials are indigenous. So cost effectiveness will be much more if we are able to make the particles to battery. So particle also we should start with.
Thank you very much. But then the first question was not just related to the analytical method, but then it is also related to the damaged cells and how one would ensure safety. With respect to that, how will we go about looking at the analytical methods is what the question was actually. Do you have any comment on this?
Yes, we do have, like the safety aspects. Maybe some of the, I will start with some of the problems. If you see a lot of the laptops will be catching fire, the mobiles will be catching fire, including the aeroplane. It was getting into problem, no? A386. So all these things, I will not agree that the battery is problematic, because the process engineering is not properly handled, as well as the overcharge protections. The cells are subjected to misuse. So if we can avoid the misuse, cells will not do problem.
And that's nicely put anyway. One last question I see on the chat box is the difference between lithium-ion capacitor and supercapacitor.
A lithium-ion capacity, that's what I was telling you. So if the anode, if I think he must be a technical person. In lithium-ion, we have the graphite material as the anode and the oxide material as the cathode, wherein in between the layers, the lithium-ion is stored. So this is one of the reasons why it takes long time for the energy to be delivered. But when it comes to lithium-ion supercapacitor, the lithium-ion capacitor, it is only the cathode they are replacing, but not the oxide materials. That means the capacity is limited by the carbon, which is part of the supercapacitor electrode. High power will be there, energy will not be there in the lithium-ion capacitor. Voltage will be there, but capacity, AH, will not be there. Voltage, ampere, hour. The voltage is there, ampere is there, hour is not there in the lithium-ion capacitor.
I think we are probably running out of time. One last question from my side. See, the charge balancing or the battery management system. So what is it that you would adopt when it comes to the supercapacitor, and has it been developed?
Whatever the charge management which is applicable for the lithium-ion cell is completely applicable for the supercapacitor also.
Okay.
So it is, we have matched, because now that we have patented, and I can also disclose it here, we have matched the carbon electrode as well as the oxide material in the cathode.
I think we are probably running out of time. There are a couple of other small questions. Maybe these questions can be passed on to Dr. Ilangovan, and then he can just send the information across.
Yeah.
Otherwise,
Sure.
Thank you very much, Dr. Ilangovan. We probably will get on to the next speaker. Thanks a lot.
Thank you so much. Thank you so much.
Thank you, Dr. Ilangovan, for making such an exuberant start to the technical presentation session today.
So that's why I combined the capacitor as well as the battery together. It's energy plus power.
Yeah, that was evident in your talk. You had both of them supporting you.
Thank you.
Yeah. Okay, so we go to the next speaker, Dr. Tata Narsingh Rao. Dr. Narsingh Rao, he has a PhD from BHU, Banaras. He was at the University of Tokyo as a postdoctoral fellow and subsequently became a lecturer in the same university in 2001. Then he joined the International Advanced Research Center for Powder Metallurgy and New Materials, ARCI as it is called, in Hyderabad in 2003 as senior specialist, and presently he is director in charge at the same center, ARCI. Dr. Rao is known for his translational nanomaterials research. He has developed novel, scalable, and low-cost processes for suspension powder production of nanosilver, nano-TiO2 for self-cleaning, antibacterial textile applications, high-performance lithium-ion electrode materials, bio and organic waste-derived activated carbon for supercapacitors, and nano-aluminium for high-energy applications. 6 of the technologies developed by his team are transferred to industry and commercialized. Other areas of his research include solar energy materials, photocatalysis, diamond electrochemistry, biosensors, devices, etc., etc. He is a mentor of Biomedical Working Group of ARCI with special focus on additively manufactured biomedical devices. He is a recipient of several awards and honors, including Material Research Society of India Medal, Tokyo University of Science President Award, Academician of Asia Pacific Academy of Materials, Technology Day National Award, and he's a fellow of the Telangana and Andhra Pradesh Academy of Sciences and has more than 175 research papers and filed more than 20 international and Indian patents. He has got a good citation index, and he has been a member of several project assessment standardization committees. A warm welcome to you, Dr. Narsingh Rao, for your presentation on supercapacitors. Thank you.
Thank you. Thank you, sir. Now, is it visible, my
Yes.
presentation?
Yes, it is visible.
And let me also check whether it is moving. Slides are moving?
Yes, they are moving, sir.
Okay, right. Thank you. So, thank you, Lovraj Kumar Memorial Trust, Chairman and other members, and my friends Basu and Sampath for kindly giving me this opportunity to speak. I also thank Elangovan for giving nice introduction and then coupling both battery and supercap technologies. So that makes my life easy. But what I'm going to talk in next 20 minutes is how to indigenize the technology, whether it's a battery or supercapacitor. And Elangovan also said that it's a material that is very key. And then even for the supercap technology, they have the turnkey solution, but they need the material which is being imported. So now I'm going to project on how we have to indigenize the material technology. So my ARCI is very well known for its translational research. It's one of the DST institutes with a mandate of transforming laboratory research into technology and transfer to industries. My next slide. So if we look at the Indian scenario, and it is very well known that we are third in ranking of our publications, but when it comes to technology, we are way behind. The reason why it is because we have a strong knowledge base and which works in TRL 1, 2, 3 level, and then we also have the companies who import the, if it is battery, for example, EVs, they import the basic cells, that is a 3.2 volts LFP or 3.8 or 4 volts NMC batteries. And I see pure EV, for example, my friends in IT Research Park in Hyderabad, they import hundreds of thousands of lithium cells, and then they make in the form of battery pack, and then again buy the BMS system and then put it and then that pack. So the companies, what they do is they bring the basic materials or the components and then assemble, and the institutes with huge knowledge, they do the research and then do the innovations and publish, but in between the gap is the engineering gap that is causing the problem in India, and we're not able to compete with the companies next to us, countries next to us. So now, how to bridge the gap. So ARCI is taking this responsibility. Of course, we're a small institute with 60 regular scientists and another 30 project scientists, but still we're trying our level best to do the job. And then whenever we find something interesting, we file patents and try to protect the intellectual property and start scouting for the industries and then see whether we can transfer the technology. But when you want to do that, you have to go beyond this TRL3. That is TRL3 to 4 is technology development, but you have to do the technology demonstration. When it comes to materials, I have to show that I can make the material, whether if it's a battery material, I should be able to show that I can do in kilogram quantities, not just few grams or few tens of grams. And when it comes to supercapacitor, for example, and then you have to show that you can make kilogram quantities of activated carbon with a unique properties and unique process which is already patented. So you have to have the scaling up capability, and you should have the innovative either material or the process so that you protect the intellectual property. For example, lithium iron phosphate, and it is a material itself is already patented, so you cannot really patent LFP. But the way to make the LFP and what are the shortcuts and easy to make and the shortcut, the easy process, low cost procedures that we adopt and then make LFP totally indigenized. And then if someone wants the technology, they can take and sell. And now LFP is already, the product patent is very soon getting expired because already more than 20 years, the initial patent. So even Chinese patents are also getting expired. So now it is a time where Indian industries can jump. So I'm going to show both two materials, how we took it to the next level of TRL67 and how it has gone to industry and then now in the process of commercialization. And then I just want to quickly take you, I don't want to spend time because everyone knows about this. So in 2005 in Forbes India, I used to show this one. And if you even your car cost, for example, E2 at that time is 8 lakhs equivalent to WagonR, which is petrol vehicle 5 lakhs. The 3 lakhs is because of batteries, and 90% of that is coming from imported one because you have to import the battery packs. But even I import and buy the car at 8 lakhs, still my expenditure on running cost for 10,000 kilometers per year is only 5,000 rupees per year, and it is 70,000, 5,000 rupees per year in 2015, but it's more than 1 lakh so per year if I buy the petrol and run my vehicle 10,000. So even I spend 3 lakhs more, I'm still okay. After 3 years, I get my money back, and then that will continue. So this is advantage of that. And imagine that if you can make your vehicles within the country, if you can make your battery packs within the country, now what they are doing now, and if you can make the cells within the country and the materials within the country, then you scale down the cost drastically, and that will make the technology competent and more adaptable. And one more key point what I want to make is that the firing of these vehicles, and just few days back, maybe 1 week back, we have Electron, the company Electron, I think, that company buses. It is an Indian company bus, but they use imported battery packs. So one bus got burnt in Mahatma Gandhi bus stop. And earlier we have scooters and cars were getting fired, and then on October 12th, when there was a fire accident happened and it became very popular in media, then we had a panel discussion about how to avoid this battery fires. And the battery fire comes, I'll get back to there when I go to next slide, why battery fire comes. So if you see the cell manufacturing and the cell, the 60% of the cost of the cell is materials. So if you can plug on, see the remaining goes in the machines, what you use for making the battery cells. But the machines, I think it will take some more time to make machines within the country. For example, we have recently in Science Day lecture, I was telling the Nobel Prize came for Raman effect, and Raman is our own man. But Raman spectrometers, we still buy with a huge cost because we don't have manufacturing technology within the country. The same way, You have to import the battery making machines, of course. And we also have a machine pilot line for supercapacitor making line. But if you can at least contribute to making the materials, which is 60%, the battery cost can come, cell cost can come by 20 to 30%. So that's what I want to insist, that material technology development is very important. So you can see here, there are various materials what you use for the batteries, combinations. You know here, lithium, if you take a reference, it is 0, and the 0 versus the cathodes are on the up, where you can choose, and lithium itself is not stable. That's why you cannot use it for several reasons. Dendritic growth when it recycled and then deposited back, or when it is very sensitive to the oxygen and moisture. So graphite, which is very close to lithium in the bottom, but its energy density is not so much. It's 300, 340 milliamp hours gram, but this is itself acts like a lithium and gives enough voltage. And the cathode side, but graphite, see, when I see the red region, that is more dangerous region where it can get prone to firing when if you don't use it properly. So graphite, fortunately, there is enough technology to make SA, solid electrolyte interface layer, which protects the graphite for firing. So graphite is no problem. And you can use also lithium titanate, Li4Ta5O12, which is 1.5 less for the total voltage. If you use graphite for LFP, it will 3.2. But if you use LTO with LFP, you get only 2 volts. But both are in white region. That means both are pretty safe. If you have a LTO and LFP cell, it is fantastic. But unfortunate thing is your energy density is poor because only can give 2.4 volts. And now people are talking about LTO versus LMNO. This is called NMC batteries, lithium, nickel, cobalt, manganese. That also gives 2.3 or 2.5 volts, which is also good. So a lot of combinations are coming. But most of the problems come here with the NMC. If you see the lithium manganese phosphate, lithium nickel manganese cobalt manganese oxide, lithium cobalt oxide, what you use on cell phone. These, as you go towards up, they're going into red region. There, even the solid electrolyte interface comes when you go to this region also, even on cathode, which doesn't happen in conventional cathodes. But when you use lithium iron phosphate, which is the one now the key material for India, lithium iron phosphate is being now explored. China, even Tesla, when they want to use sell the cars in India and China, they want to use the LFP cars because it is very, very safe. The oxygen cannot escape so easily because in the phosphate network, unless the cobalt oxide, what is there in NMC. So all these issues are there. So LFP batteries are very, very important. If you ask any company in India who are establishing battery companies, they say that I want LFP. So indigenizing the LFP material for the supply chain in the future, next 2 to 5 years, when all these battery plants come, they need the material, LFP. And LFP, if you depend on imports, all over the world, the demand is growing very high. So the supply chain will come. So even you don't want the cost effectiveness for the LFP, but you need to have LFP supply within the country for the sake of production and then meeting the demands of our own car companies. So how to do that one? It is very easy to make lithium iron phosphate. Anyone, high school kid also, if he knows a little bit of chemistry, you can take the raw materials and then mix it and then do the solid state synthesis. But LFP, lithium iron phosphate, is insulator by itself, so it cannot draw the current. So LFP has to be coated with carbon. And that's the first thing. So each particle of LFP is coated with the carbon to draw the current from the electrons what are generated because of lithium intercalation, deintercalation. That has to go to the current collector, which is the aluminum or copper foil, whether it's a cathode or anode. And second, you have to make the size of the lithium iron phosphate into nano size because it is insulator, the lithium ion cannot diffuse to the electron cannot diffuse to long distance. So the diffusion length will come down when you have the particle size. This is the one key challenge for making this material. So we have established the method by solid state synthesis and then shown here that we are on par with any imported material. We tried with Indian Clariant and Japanese companies, Toda and all, and then we established that. But the cost is still not good enough because 100 lakhs we spent on the milling unit, which is an imported German one. And now can we do and then optimize on an Indian one? And we made a treat and we did it for 3 lakhs, and then we got the same kind of properties here you can see. Now the cost reduction. So unless you do the cost reduction, then no company will come forward. So that is what is the adoption of technology. Now what we did is we are doing 1 kilo in the treater made within the ARCI. Then we went to a powder metallurgy company and 20 kilogram treaters they have for the powder metallurgy. So in the practical conditions, we got it done, and then we had to do fine tuning, a little bit of process parameters, and finally we made it. So now with 10 to 20 kilos production capability, what we did is we signed agreement with the company, metallurgy company, who keep supplying, helping us in demonstrating the high scale production with our basic know-how. And finally, 3 months back, we transferred this technology to Alox Minerals, a Telangana company, who will be setting up their production plant for supplying this one. So this is what is the battery materials. We also have enough similar technology with lithium titanate, fully developed and then much cheaper than lithium iron phosphate. And then we are waiting for some customer to technology receiver, and then we have some contacts with that. So we demonstrate at different levels of either in the form of fan or some kind of lighting, and then some small electric bikes also we demonstrate. So now coming to Supercap, same thing. Supercaps are very well known, and Dr. Ilangavan nicely explained the difference between the supercap and battery. And he also said that the material for the supercap is also key. And it's not so difficult to make a material. And Maxwell is one well-known company, is American company, which Tesla bought now. And they import the raw material, it is YP50, it's activated carbon from Kurare, Japan. And Kurare makes this YP50 from coconut shells. And coconut shells, they don't have enough coconut trees, and they get from Sri Lanka and India and other countries. And then they convert it into the carbon. And their technology is how to make it nanoporous with designing the nanopores suitable for storing this energy. That is the key technology. It is not converting coconut shell to carbon. And that is protected with a portfolio of patents. So now what we did is, can we do something different? Because my problem is, can I make a material totally indigenized and intellectually protected? So what we did, initially, this were already, he mentioned battery versus supercap. I don't want to talk about that. And supercaps, they have high power density. They can be charged in seconds or minutes, unlike batteries, which takes a long time, but they have battery has high energy density and supercap high. But in China itself, they have the public transport buses, they have plenty of lithium, but still they use this technology for their public transport because they just get charged very fast. So the moment, you cannot use a car with supercap because you cannot travel long distances. But a bus would travel for 5 kilometers, 10 kilometers. They can use supercap, and whenever the bus comes to the bus station, the connectors go and touch the cables, and it gets charged in minutes by the time passengers get in and get out. So this is what already happening, and then several countries are using this for the public transport. And what we did is, can we do this within the country? And initially we started with jute sticks, and jute sticks are useless material because once you take the jute skin for the jute bags, the sticks are only firewood, but they're very light weight and then cellular structure. And then we converted under nitrogen atmosphere to carbon with proper KOH activation process. We get the graphene-like carbon with very high 1500 meters square per gram above surface area. And then we demonstrated that its performance, you can see here, is on par with YP50, the cyclic voltammeter. You can see that. And then the cost is pretty low. So we did it and then demonstrated a supercap of 20 farad. But that's not enough. If you want an electric vehicle to use any supercap, it should be more than 1000 farads. So we were looking whether can we do that. We have a good beginning, but the jute stick carbon, because it has only 20% yield. When you take 1 kg, you'll get only 20% of that converted to carbon. So that's not enough. So now in the meantime, HPCL has listened to us, and they understood that we have the capability of scaling up of the materials and designing the scientific part of the material suitable for supercap. Then they were asking that, can you convert petroleum coke into the activated carbon? Yes, petroleum coke has got more than 80% carbon, and it is a waste byproduct of the petroleum refineries, which has got 5% sulfur, and it is used for the cement and steel industries. They burn it as a low-cost fuel, and in fact, we are importing petroleum coke from US and other countries because we want a cheap fuel, but there was a ban few years back. Even then, our refineries produce a lot of petroleum coke. So the HPCL group trusted us, and that they, in fact, funded us of 1 crore for setting up a pilot plant and then converting this petroleum coke into the activated carbon. We did it. You can see that after fine-tuning, we got a graphene-like layers and then very high surface area and kilogram. Now I don't have the problem of yield, and I can make kilograms of this because if I remove 10-20% of the carbon by etching during the process, I can still have huge quantities. And I'm again with a device which is made up to this. I said electric vehicles need more than 1,000 farads at least to drive and support any EV. So we made 1,200 farad supercapacitor with on par with Maxwell. And with the help of HPCL, their financial contribution significantly, and the material sourcing and their expertise. So we made the pilot facility, and then some of the equipments we made indigenously actually, because for supercap, some equipments we forgot to bring it because the battery equipment we bought, and then some we made it indigenously, and we understood that equipment also can be made in India because people think that we cannot make it. Now we proposed a 50 crores project to DST to make total battery line within the country at ARCI with support of 10 crore support came from the company, because indigenizing the equipment, unless you indigenize the equipment manufacturing in the country, you can never compete with imported batteries from China. So that is one thing what all the industry should do, and then we are doing that for the first time, and we're going to do, because our initial success tell us that we can do that. And now with partially indigenized equipment like this in-house design of flattening machine and all this, you can see that we have a green one ARCI supercap and blue one is Maxwell. We're on par with both in the properties, and we are on media, and then some companies start coming up. So this is what my colleagues, and then we work on that. And what we did is HPCL said that you have to demonstrate a bicycle with these supercaps. So 48 volts motor has to be run with supercaps. That's not so easy. That's why I said that you need at least 1,000 farad supercap. Otherwise, it's only the supercap cannot have more than 2.5 or 2.7 volts. So you need at least 50 to 20 supercaps of that to get enough energy density. Even you want to run 2.5 kilometers. So now you see it's ARCI's bike. Initially, this bike was done with the Maxwell supercaps, and then we have done with our supercaps. You can see the closure of the HPCL project, successful deliverables of a supercap bicycle, totally driven by our that time director. Unfortunately, is no more. Is so active, Dr. Padmanabhan. Due to COVID, he lost his life. So, but with his energy and enthusiasm, we got to this, and we also have the companies coming forward with the lead-acid battery-based auto rickshaws, because if you go to Varanasi, all the auto rickshaws are lead-acid based. Because for auto rickshaw, you don't need to worry about too much speed, or there is no driving range anxiety and all. So they are very happy because they cannot spend more than $1 lakh. So now, but the problem with lead-acid batteries, when you drive uphill or when you do the starting or when our speed breakers, they need to draw very high current you abuse. So your 2 years guarantee will come only 6 months. That's why several buses on IIT Chennai campus, when they started, they were shut down because the batteries were failing because too many speed breakers on the IIT Chennai road. So now, if you have the coupling of the supercap pack in line with that, and it takes all the peak powers, and then we have demonstrated a auto rickshaw, a Hyderabad-based company collaborating with us, and with our supercap pack, and we are now generating data, and they want to collaborate, and probably some people are coming forward now to indigenize that. We have the technology to make. I don't call it technology. Making a supercap is not a technology, because you buy the machine, you know what is only you have to fine tune and then make a supercap. Now I have a supercap. But I cannot patent it, no companies, but I have patented what is inside and which is the key of our technology. That is with the help of, we have partners with HPCL. And with this now coming, like Elangovan said, Sampath, you are looking for me to stop. Give me 1 more minute if you don't mind. Shall I? Take 1 minute?
Go ahead.
Yes. So this is the paper which is about to come, energy, one of our students published. So one way is that lithium-ion capacitor and another way is pseudo-capacitors. Pseudo-capacitors, not much attention is given because it is done in the aqueous alkalides. But if we can choose the right electrode material with higher over potentials, like in the case of manganese oxide fine-tuned and deposit on the carbon, you can go beyond 1.5. Now I have a pseudo-capacitor of up to 2 volts. I can cycle it, which is reasonably okay. Now it is more than lead acid battery voltage. And then you can see here, what I'm doing is I take an electrolyte with a redox couple, which has got very high cycle stability. I went up to 10,000 cycles with only 80% retention, but that is good enough for a super cap. And then 134 farad per gram at 3 ampere per gram current density. And I am talking about equivalent capacity of a non-aqueous capacitors, what we talked so far. And then the moment you have an aqueous electrolyte, you don't need to worry about firing. You just run the way you are doing your lead acid battery. And then I could go up to 10,000 cycles. And only thing is you need more numbers because your voltage is less. But that's what happening in lead acid also. So we're trying to do whether we can equate to the lead acid with these super caps, but with very high power, so that it doesn't die. So that's what is the next one, but is my students' work. But we are very happy with this. Thank you so much for all of you for paying attention. And thanks to all my people, scientists, engineers. Engineers are required. It is not a single one's job. You need engineers to fill the gap. You need technical support. You need strong PhD students who does the fundamental contribution. Without them, we're all zero. So, and then we have funding, of course, HBCL, NSTL, DRDO, DST and all, and industry partners who demonstrate our technology at the actual practical scale. And now they also get share in our technology transfer. We signed agreement for 5% of transfer of technology, 40 lakhs. We already non-exclusive, we transferred LFP, and then 2.5 or 2 lakhs, we already transferred to them. And there are 3-4 companies, big companies are coming for LFP. Thank you so much for your attention. I'm done. Sampath, over to you.
Thank you very much, Dr. Tata Rao. I think it is a wonderful presentation. I have 3-4 questions. I'm going to read out the questions. I would like you to be very precise so that we can stick to some time.
Okay, I promise.
Okay. So the first question is related to the yield of activated carbon from petroleum coke and also the coconut shell. Is there any information on that? Yield.
Yeah. You want me to compare?
Yeah. Is there any information on the yield?
Yes, we ourselves did it. So it's only 30% for the coconut shell and it's 70% for the petroleum coke.
Okay, that's good. That's good.
And the second question that I see is LFP during electrode preparation can use normal aluminum foil rather than carbon coated aluminum foil. Can you clarify this?
So we usually quote carbon coated aluminum foil because when you use normal aluminum foil, what happens is you cannot, when you increase the loading, because your loading of the material tells you how much energy density of the cell. So your loading, as you increase, then it starts peeling off. So if you have carbon coated electrode, the aluminum foil, that gives very nice loading onto that.
And the next question is related to some fundamentals. Which supercapacitor is better, electrostatic capacitor, electrochemical capacitor? When they consist of the same material, how do you decide the polarity? I don't quite get this question, but anyway, what is the electrolyte in supercapacitors?
Electrolytes in supercapacitor is two. One is in the aqueous one, we have KOH based, and in non-aqueous, it is tetraammonium borofluorate in EC or acetonitrile. And even sodium perchlorate also can be used in propylene carbonate or acetonitrile.
I think the previous question on the polarity was if you have a symmetric capacitor where you have both electrodes the same, how do you decide the polarity is what the question is.
I really don't understand the question. If you can understand, you can also answer your supercap. Help me.
No. It's he just talks about the symmetric capacitor and there is no real issue there.
Yes, yeah.
There are a few other questions. Let me just, LFP synthesized by flame spray pyrolysis or solid state milling method. Which method did you use?
Yeah, so we did actually, maybe they are very familiar with our technology, it looks like, following us for more than 10 years. Because flame spray pyrolysis was the beginning what we did, and then we got excellent properties. But flame spray pyrolysis will give the lithium and phosphate, but there is not carbon coated. Then you have another step to coat the carbon. So that is increasing the cost. Although we got wonderful results, then we gave up. Then in solid state, what I showed in the first few slides, it is a single step method where the carbon is in situ modified and then there is no second step for that.
Okay, the performance comparison between LFP and Lfmp.
See, they both are two materials where NMC is used for the high energy density and then long range for the electric vehicles. LFP is more safe and low cost, and all these are the advantages with LFP. So there's no direct comparison. It is lower voltage because 3.2, whereas that gives 3.8 to 4, depending on what kind of combination you are using the NMC, whether it's 532 or something. Is that one what they are asking, Sampath?
I guess so. I guess that's the comparison that is being.
Okay.
They're asking LMFP and LFP.
Lithium manganese phosphate? You mean?
LFP.
So, see, lithium, we tried all phosphates by flame spray when we were trying. But in manganese, you have the John-Teller distortion problem. So, after a few cycles, it dies. In fact, we got initial very high energy, specific energy, but it fades away very fast. So, we tried to establish, but we thought we have to scale because our goal is what is working, that you have to indigenize. So, we are focusing that we succeed. But we stopped that. It may work if you have proper kind of doping or coating or whatever. But we don't.
We'll just stop with this last question. Do you have any work on liquid metal batteries?
No.
Calcium alloy as anode, molten salt, electrolyte, antimony particles as cathode.
So the questions, see, ARCI, even our students, when they work, we focus on their research towards whether some technology will come or not. Because every time we have to show how many patents, how many papers, and how many translatable technology. So we don't venture into something what we are not good at, or we don't venture into what it may not work, it's not well established. So we keep collaborating with people like Sampath IISc or IIT people who are fundamentally very strong and come with new compositions and all. And if they are working at that level, we collaborate when we translate and then scale it up. That's it, because that's how we work.
I guess probably we'll just close it.
You'll have to,
and then get on to the next speaker. Thank you very much, Dr. Rao.
Thank you, sir.
Thank you.
I'm coming out.
Yeah, it's a very interesting and a very comprehensive presentation, I must say. We have the next speaker, Professor Pratibha Sharma, who is going to speak on metal hydride storage for hydrogen. Professor Pratibha Sharma is professor in the Department of Energy Science and Engineering at the Indian Institute of Technology, Bombay. Her research interests include hydrogen storage materials and systems, hydrogen utilization, low-cost earth-abundant materials for photovoltaic applications, and materials for biomedical applications. She has worked on various types of hydrides for solid-state hydrogen storage, their modifications, catalysis, support, and tailoring the reaction mechanisms. She has been working on simulation, design, and development of hydrogen storage reactors for various applications. She is currently on the editorial board of international journals, etc. And she has supervised about 16 PhD students and has more than 90 referred international journal publications and 4 patents to her credit. Has been awarded the Outstanding Service Award by the International Association of Hydrogen Energy. And she is leading several multi-institutional R&D projects on hydrogen systems development and integration for different applications. These projects have several IITs and industries as partners. She has established a multi-institutional R&D center on hydrogen at IIT Bombay with DST funding, and has international collaboration with several countries, to name a few: Canada, Japan, Australia, Canada, South Korea. Over to you, Professor Pratibha Sharma, for your presentation.
Thank you. I will share my screen.
Yeah.
Yeah, is that visible?
Yes, it is.
Yeah. Thank you. Thank you, Professor Deshpande. I will be talking about the different metal hydrides for hydrogen storage application. When it comes to hydrogen and its usage, the major challenge, we know that, just to give a brief introduction, the major challenge is its storage, and the density of hydrogen, since it is very low as compared to the other fuels. On a mass basis it is very high, but on the volume basis we can see that it's very low as compared to the other fuels, whether it is methane or gasoline or diesel. And if the options that remains is either you pressurize it to a higher pressure, whether it is 200 bar or 350 bar or 700 bar, which the commercial cylinders are available, or you liquefy it to a lower temperature, to the 20K, you have to cool it down to 20K, or then you have another option where you can get a higher density when you store it in the solid state form. So my focus of today's talk will be, I will be straight off going on to the solid state storage of hydrogen. Now, as compared to the other methods, solid state has an advantage. Now, what advantage that has is, in gaseous state storage, since the density is low, you require very high pressure tanks, and the commercially available type 3, type 4 tanks are 350 bar or 700 bar pressure tanks, and they use special composite fiber materials, and as such the cost is higher. At the same time, when it is such a high pressure, safety remains a concern. The other option could be you cool it down to 20K and then make it into liquid. So the density improves considerably. We can see that in these numbers. But then the process of cooling it down or making it liquid hydrogen is highly energy intensive. It takes up about 30 to 40% of the energy content of hydrogen. And at the same time, these require super insulated vessels, and whatever good insulation we may use, there will be losses involved. So there are boil-off losses. And at times, even if you have a full tank and you leave it for a few days, then you will find it vacant because of these boil-off losses. So this can be particularly useful when you want to use it for in a short duration. You want to use it after refilling. However, another option that I'm going to discuss is the solid state storage. This particular method, this is a higher volumetric energy density, and it is the safest method because you are not dealing with such high pressures or liquid, such low temperatures. At the same time, the challenges are also there that we will see. So you do not require neither a high pressure or a low temperature requirement is there for solid state storage. Now there are different types of hydrides which can be used to store hydrogen. Like there are metal hydrides, which are the well-known systems with known materials commercially available. Then there are other classes like complex hydrides, chemical hydrides. Then there are different solid solutions which you can use, or high entropy alloys. Now at IIT Bombay, we are working on all these type of materials. Today I will just take certain examples, quick examples of some of these materials and the systems work which we are doing at IIT Bombay. So we work on the catalysis, support materials, how we can enhance the performance basically of these materials. We do a lot of kinetic modeling and systems development. So if we start with the metal hydrides, then there are different classes of metal hydrides. These are either like the intermetallics, wherein you have a combination of a metal element A and another B, where these can be alloyed together to form either AB, AB2, A2B, AB5, or A3B7, several other alloys. And each of these, they have a separate characteristic. Just to give few examples, like the AB5, which is the well-known example is lanthanum nickel 5. It has advantages that it has low hysteresis. Whatever the charging or discharging, you can say in easier terms, it is complete without any memory, no memory, so no losses. It is easier to activate, and it is tolerant to the impurities if there is any impurities in the material as well as in the hydrogen gas stream. But the problem is the capacity is lower and the cost of the raw material. Then there are materials like AB2 type of hydrides, zirconium chromium 2, that has an advantage that they have a higher capacity compared to the first class, which I just mentioned, AB5. But then the problems are that they are difficult to activate. Activate means the first time when you are putting in hydrogen, there is a lot of resistance. So you have that there is an activation barrier that you have to cross through, and that could be by means of either subjecting it to high temperatures or pressures. Another class like AB, where the cost is comparatively lower and they can work close to room temperature, but the problems remains again the difficulty in activation. Other than the intermetallics, there could be solid solutions. The well-known one, titanium, barium, chromium, which has a higher capacity, but then the cost again is a challenge. And then the problems associated are difficulty in activation. What exactly we require from these materials is the material which operates close to ambient conditions, 1 to 10 bar pressure, absorption, desorption, and room temperature operation, 25 to max say 100 degrees centigrade, so that we can couple up this with a polymer electrolyte membrane fuel cell, and the waste heat of PEM could be used for desorption of such materials. But all these, all the elements which are there in the periodic table, although they form hydride, but then many of these hydrides are unstable hydride. Either they decompose very easily or you require a lower temperature. So what you need to do is you have to stabilize those hydrides to increase their stability. Or else these hydrides are very much stable, so you require very high temperatures to get hydrogen from those hydrides. So you have to make them destabilized. Now there are several strategies which could be followed in order to do that. Either you reduce the size, particle size, nano size it, you do nano confinement, or you can alloy these, make several alloys, you can add certain additives, you can generate certain defects so that the diffusion of hydrogen gets easier. And all these can be done in order to either stabilize or destabilize these hydrides and tune their thermodynamics. Now, the essential thing here in terms when you are using hydrides is that you have to tune the required temperatures and pressure so that the material it absorbs and desorbs at reasonable conditions of operating temperatures and pressures. And there are vast applications of these metal hydrides, and we are also working on a lot of such applications. Like it can be used for hydrogen storage, sensing, battery, we know that nickel metal hydride. These can be used for smart windows, hydrogen purification, catalysis, thermal energy storage, hydrogen compression, hydrogen purification. Now, if we quickly see at 1 bar pressure, as a function of temperature, absorption temperature, the capacity of storage of such metal hydrides, if we try to put them together, then we can see that there are different regions of different metal hydrides. There are regions wherein the metal hydrides, they have a very high capacity, gravimetric capacity, but at the same time a broad window of operational temperatures, which can be even very high, beyond even 200 degrees centigrade. There are very high capacity materials like magnesium and magnesium based alloys. Although they have a very high capacity, it can go even up to 7.6 weight %, but then the operational temperatures are beyond 225 degrees centigrade, 230 or 250 or 300 degrees centigrade. And there are solid solutions which are having reasonable capacity, at the same time they have a reasonable operating conditions, and various other hydrides as well. Now, the major challenges if we look at these materials is, although they have large advantages, because these materials when they are used, they have a long cycle life. You can even charge and discharge with hydrogen these materials for thousands of cycles. So they have a better safety, because if there is a leak in such a tank which is storing metal hydride, in that case, the reaction of hydrogen leakage, that is hydrogen coming out of these materials, is an endothermic reaction. And in that case, the reaction will itself stall, and as such, there won't be a threat of any explosion or a catastrophic event. So these are safe to operate. They operate at conditions which are close to room temperature and pressure. They have higher volumetric density, and you can, there are materials which can be completely discharged. So whatever you have put in, that amount of hydrogen you can take back. Now, it's also the thing that the material, a typical material when it comes to metal hydrides, we say that the maximum that they store is the traditional materials, and most of the materials they store is 2 weight %. So we can do that calculation that metal hydrides which are operating at room temperature condition, at the ambient conditions of pressure, they can be cost competitive to 700 bar pressure tank. Now, due to the lower operation, we can say either still we can get a higher volumetric density, because the volumetric density of metal hydrides is far ahead as those of compressed hydrogen tank. At the same time, we are operating at a lower pressure. So why we should go for a compressed state storage, although it has benefit, my later speaker will talk about it. But then when this requirement, when you want to couple that storage system with a fuel cell which operates at whose inlet pressure will be 2 to 5 bar, why we put extra energy and cost in compressing it to so high temperature, so high pressures? where we can use such storage tanks and we can still operate at a reasonable performance. Now the problem lies is with all these advantages, still the problem is that the materials, these metal hydrides which are operating close to the ambient conditions, they have a lower capacity. While those materials which are operating at a higher temperature and pressure, they have a higher capacity. So what is required is to come up with certain materials which have both a higher volumetric capacity at the same time which operates close to the ambient conditions of temperature and pressure. Now, other than these metal hydrides, there are various other metals also. They form hydride. There are different non-metals as well, like the carbon-based materials, different metal organic frameworks, cobalt organic frameworks. They can also store hydrogen by physisorption, and they have a very good kinetics also. Kinetics of uptake and release of hydrogen. But the problem is they still are operating for like weight percent, their capacities are less than 2 weight percent. At the same time, the temperature required, because the bonding is very weak, so the temperature required is lower temperature, 77 K or close to that. So another option could be use of liquid organic hydrogen carriers, which are a high energy density materials. Again, hydrogen capacity is higher, like ammonia and cycloalkanes, which are also promising. But then the problems are that putting back that hydrogen which you have taken out is an energy intensive and cost intensive, that is the biggest challenge. At the same time, the stability, energy efficiency, and the reversibility of these materials, an appropriate catalyst is required if we want to take them for hydrogen transportation. Now, among the possible options of the metal hydrides is, we can have either alkali and alkaline earth metals forming their hydrides, ionic hydrides. Examples are like lithium hydride or sodium hydride, and then in them the hydrogen exists as a hydride, H-. We can have even covalent hydrides, like example being lithium amide or ammonia. They have high capacity, but the hydrogen here is partially positive charged. And similarly, we can have complex hydrides like sodium alunate or lithium borohydride, different alunates and borohydrides, which already have a high capacity, and then they have a partial negative charge, delta negative charge. Then there are interstitial hydrides, like the ones which I have already told, like the intermetallics. They can store hydrogen when they are forming metallic bond. Now, each of these, they have their own challenges. Some form very strong bond, like in case of complex hydrides, so that if you are taking out hydrogen, the dehydrogenated product is very difficult to regenerate. So the spent fuel and getting back the initial compound is a problematic, is an energy consuming process. So what can be done is, we can have a combination wherein both these components could be put together, so that to have a mixed hydride, and that could favor a better, we can get a better thermodynamics using those class of materials. Now, what exactly we look at when we talk about metal hydrides is that these metal hydrides should be easier towards activation of the material, that the uptake of hydrogen as well as release of hydrogen, also known as the first hydrogenation dehydrogenation cycle, that should be easier. It should not require very high temperatures and pressure. At the same time, the uptake and release should be faster, so the rate should be higher. They should have a reasonable heat of formation of hydrides. Now, this becomes very important when we talk about large-scale systems, large-scale solid-state hydrogen storage systems, because one process is exothermic, the other process is endothermic. A lot of heat needs to be supplied and taken out. So thermal management becomes important. So in that case, the metal hydrides which have a heat of formation which is optimum, somewhere 30 kilojoule per mole, that would be very good to operate with. These materials should be stable under repeated cycling. So cyclability is important. They should not get poisoned by the impurities, and the safety associated with the use of metal hydrides when you are operating with such tanks is also important. At the same time, cost. To give you example of BCC alloy, like titanium, vanadium, chromium alloy, it has an advantage that the absorption takes place at a lower pressure, 20 bar, and at room temperature. It has a faster kinetics, and theoretical capacity is 4 weight percent. You can have wide range of alloys by changing the composition of these materials. The problem remains is they have a sloping plateau and an incubation period. Now, how you can do that? Like if we try to address the incubation period, which is in the first hydrogenation cycle, that is the activation problem, we can either use suitable additives, or heat treatment or ball milling. Like one example I am quoting here, that this alloy with say different dopants, with the different substitutions of say zirconium nickel or zirconium individual, we could get a capacity of 3.76 weight%, which is considered to be considerably higher as against the other metal hydrides, which maximum they gave 2 weight%. And it has a faster kinetics as well. And that incubation period was not there, which in the bare or the pristine alloy, it remains for hours of operation. Herein we could get in fractions of, we could get in a few seconds, we could activate that alloy. So with the suitable doping, we can change the characteristics of the alloy. Now the another class of material is well-known example of iron titanium, although this has been studied, but still there are several problems associated with that. It is a good alloy in the sense it is cost effective. It can be operable under temperatures and pressure conditions which can be easily coupled for a PEM fuel cell with a PEM fuel cell. But the problem remains is that it has plateau instabilities. It has require an activation step which requires high temperature and pressure. Now what can be done is we can dope it with various other dopants in small quantities such that it can be made easy to activate. At the same time, we can get many practical applications using this particular alloy, and we can use even industrial grade materials. So, and then we have also studied, so this alloy we have extensively studied. We have seen what is the effect if the equimolecular instead of stoichiometric, we go for non-stoichiometric composition. What if we substitute one of those? What if we add the catalyst? So it is like, if it is pristine, there is no activation taking place in hours. But as we dope it with different elements, then we can see that the activation gets very faster. And we can do that activation, which earlier it was like 400 degrees, 600 degrees, you have to heat for 12 hours. Now we can do at room temperature and at 20 bar. So there is an industrial partner and a UKTR, Canadian university, involved in this work. So this was some examples of one class of hydrides, which are metal hydrides. The another class is like chemical hydrides, wherein they store hydrogen, which is much larger than the conventional material, whether it is a physical form hydrogen like liquid hydrogen or the adsorption way of hydrogen, carbon nanotubes. So these materials can store, quantities of storage is very high. So now here we talk about 19.6 weight% as against 2 weight% that was in case of metal hydrides. But if it is so straightforward, then we could have found the solution. So there are disadvantages still, that the hydrogen which we are getting is not pure. And the problem lies with the regeneration of these materials. So these materials, they give hydrogen in steps. And like in the first step, 1 mole equivalent of hydrogen is released. In the second step, 2nd mole, and in the last step, 3rd mole, which takes place at a higher temperature. So why not to take an advantage of only using the 2nd step and get a 13 weight% hydrogen from this? And then we can also suppress the unwanted desired products which we are getting, like the borazine, ammonia, and diborane, which could be poisonous for various other applications. And that we have been trying, that we have been doing in our lab. And we have seen that with the different dopants, we were able to suppress the unwanted product to make it zero. Although the release of hydrogen decreased, but that we were able to, with the different additives, we were able to retain back. And now what we are doing is working on the regeneration. And finally we could achieve with the regeneration is in a so these materials, they regenerate again in different steps. So you cannot do that on-board regeneration. It has to be 2 or 3 step regeneration. Now we are able to make it a single step regeneration, and the yield that we could get is 85% yield in the regeneration step in a single step, 1-pot synthesis and dehydrogenation. So this is like what we were able to do that. So instead of having multiple steps, we just dehydrogenate it and put the hydrogen back so that this could be suitable for on-board application, and still we can get about 13 weight% capacity with such materials. Another class of materials which are known for their higher storage capacity is like the various borohydrides. Now these borohydrides, we can get hydrogen either by means of thermolysis, by heating them, or by putting them in water. So when you use thermolysis, the temperatures are higher. So sometimes like the hydrolysis favors the reaction. You can do that at a room temperature. But the problem remains is like the catalyst is required for this reaction, because this is a spontaneous process. You have to slow it down. Sometimes the reactions are very fast. Sometimes you have to slow them down because you do not want instantaneously all hydrogen to be released. So you have to change the pH of the reaction, and then you have to have a catalyst to get it at a desired rate. Excess amount of hydrogen, solubility of the compound which you are getting, these are the other bottlenecks. But the advantages with this system is that it is a non-flammable, stable system which has a stable byproduct, and this is an environmentally safe method of hydrogen storage. Now, what we do at our place is we start from scratch, from the atomistic modeling, from the DFT, from atoms level. We take the material to hundreds of kgs of preparing hundreds of kgs of material. From a system design at a computational level, we fabricate such systems to large scale, and then we do performance analysis. So in our lab, we are doing materials as well as systems development right from scratch, taking to large scale. So we start with the parent alloy, whatever alloy we have decided for working on. We do a lot of DFT to look at what are the structures, adsorption energy, charge transfer processes, and the stability of that alloy. We put in hydrogen in such systems, and then we see the study which are the favorable places where hydrogen can substitute, how much amount of hydrogen we can get, what is the storage capacity, and then we modify such systems by substituting with different metals, different elements. Again, we do all these calculations. What is the binding energies of these systems? What are the charge transfer that is taking place? Density of states? And what if we substitute by more than one element? And what is the capacity which we are going to get? Once we have optimized a particular material, then we go for a large scale synthesis. First, we synthesize on 5 to 10 gram scale, and then we go for 10 kgs of alloy synthesis. And what we start with is an industrial grade raw material. This is very important because the cost, as my previous speakers have already mentioned, that the two things in materials development is the availability of material within the country, and the second thing is cost. So what we are looking at is the materials which are available in the country. At the same time, the cost of such material should be lower. So we start with large scale synthesis from the industrial grade raw material. Definitely there will be impurities. We study the effect of impurities in these material in the hydrogen storage capacity, how that degrades, but still we were able to get very good capacities, systematically studying and taking care of the effect of impurities. Once we have the material synthesized, then we go on for large scale systems development, and there we take care of the various heat transfer mechanisms. The reason being the absorption of hydrogen within the metal hydride, it is an exothermic reaction, and a lot amount of heat is being released. When it is say 5 gram, 10 grams, that is not of much interest, but when it is tens of kgs or hundreds of kgs of such material in a system, then the tremendous amount of heat is released, or you have to supply that heat. And if you are not doing a proper thermal management, the reaction will stop. At the same time, you will not get the amount of hydrogen which is stored in the reactor. You will not be able to take it out completely. So we work on enhancement of thermal conductivity. We work on enhancing the heat transfer area, improving on the heat transfer coefficient as well. Just to give a quick glimpse of the work we are doing, we start from the DFT analysis, designing the material, making it on small scale, then making it on large scale, taking from the computer to the lab scale to an industrial scale system. So this is how we go from material, then we go on to the systems design. We do a lot of simulation modeling and optimization to come up with a heat transfer arrangement with heat exchange area with different types of arrangements, so that the system performs well when integrated with such materials. And finally, we go for a fabrication. So it is like the selection of material, tuning the properties of material to improve the performance of material. Then we go for large scale synthesis of material, designing of the tank, and then finally developing such a system and analyzing the performance. Just to give brief glimpses of the different type of heat exchangers we have worked on. We have worked on like bifurcating type of fins or multitubular structures, hexagonal fin network or helical tubes. And we have done a lot of simulations and optimization on these. So we have several papers. If somebody is interested, they can go into the details of this. Some of the systems that we have developed, a smaller system, 5 kg system, which can store 5 kg of alloy, a 10 kg system, a 25 kg system, a 50 kg system, another 50 kg system. Some of the systems, these are customized for various applications. Like one system is for ISRO, we have made and designed, and these can store, we have demonstrated systems which can store 1 kg of hydrogen. And then we also integrate them for various applications. Like one of the applications we are focusing on is thermal energy storage, wherein you have two different metal hydride beds, a high temperature metal hydride bed and a low temperature metal hydride bed coupled with a solar collector, wherein during the daytime when sunshine is there, then you dissolve the high temperature metal hydride using the heat which is available, and then you store that much amount of hydrogen in a low temperature metal hydride bed. At night time, you can use a low grade heat, and then you can dissolve that hydrogen to generate a high grade heat. So this is like can be integrated with thermal energy storage system. They are working on various other applications, like we are working on hydrogen purification, hydrogen compression, vehicular application, and backup power using these metal hydrides. So this is the large scale. This is an equipment which can synthesize in one batch 10 kg, we can synthesize in 2 to 3 hours. So in one day, we can have hundreds of kgs of material. This is the earlier shown image that we have various different reactors wherein we can store from very small amounts. Maybe we can store from few grams to a kg or more than that of hydrogen in these systems. Thank you. So this was a very quick overview of what work we are doing.
Thank you very much, Pratibha Sharma. Wonderful presentation on hydrogen storage. I have several questions which I'll just read out. Maybe you can reflect on some of them. The hydride formation, is it spontaneous? Gives free energy change negative is the question. And related question is, what is the volumetric energy density attainable through metal hydrides? You can possibly take these two first.
Yes. So the delta G is negative. Yes. For some of these chemical hydrides, as they are kept in the environment or as they are exposed to environment, they start dissolving. For them, these are unstable. So it is like when we are talking about materials, we have a wide class of materials. Some of these materials which are you have to even keep them at a lower temperature so that they may not release. They are spontaneous. But then some of the materials you require a lot of activation energy to make them to dissolve, like temperatures as high as 300 degrees centigrade. So they are not spontaneously dissolving. Onto the volumetric capacity, in general, the metal hydrides, they have more than 100 kg per meter cube, 150 kg per meter cube.
And this is a general question. Is it necessary to have solid state storage when anyway you cannot increase the percentage storage? What's the motivation?
I have already mentioned the various advantages as against the other methods, and that makes it quite promising.
I guess so. And is it possible to store hydrogen in flat-rate hydrates?
Pardon, please?
Flat-rates, metal flat-rates you have? Flat-rates?
Yes, flat-rates. Yes, people have been working on, but in our group, we are not working on flat-rates.
And the next question is related to the purity of hydrogen. I think you did mention that in the solid state hydrogen storage system, will it affect the cycles? Will it affect the system in any way? The purity of hydrogen that you can get.
Correct. So actually, there again the answer will be generic in the sense that there are metal hydrides. Like in the introduction slide I mentioned, there are certain class of hydrides which are too much affected by the poisoning or the any other gas which is present in the hydrogen. But there are certain hydrides which can be even used for purification application. Like they do not get poisoned, so they can be in fact used to separate other gases from hydrogen. So there are both type of materials which get affected, which are not getting affected by the different impurities present in the gaseous stream.
Next one is related to some experimentation. How do you get the amount of hydrogen absorbed by the parent metal? How do you measure it? And what's the instrument that you use?
Okay. Actually, we have several indigenous made. So this is a well-known system which all the people who are working on hydrogen storage, they have that. This is a Sievert type equipment. And we have several of such indigenously made, designed and fabricated by us. And we have automated ones also. So these you have to fabricate on your own.
This is an interesting question. Is there a possibility of hydrogen grid, like electrical grid in the country?
Yes, so it's actually a pipeline transport which is being looked at in the Western countries, but that may take time. The reason being, at present, what is being looked at is blending of natural gas with hydrogen, which IOCL is already taking up several projects in it. But the hydrogen-based pipelines, these are highly capital intensive, and the cost required, because they are the special materials which will be required for transport of hydrogen. So it may come up, but may take some time.
The two most simple questions, I think, how much kgs of hydrogen would be for 100 kilometers of one e-rickshaw? Is there any back of the envelope calculation?
Typically, it is like 100 kilometers needs 1 kg of hydrogen. So this is the rough estimate. And depending upon different materials, as I told you, starting from 2 weight percent to 20 weight percent, you can calculate how much amount of the alloy weight will be required.
I think one last question, is it possible to disperse the metal hydride in some medium and improve storage? To disperse the metal hydride in some medium.
I think that is not required because you can easily handle them. That dispensing in some medium is required when these are very much prone to environmental degradation. So you want them, but this is like the storage systems that I have just already shown also. You just require a tank to fill in and then use, and so it becomes like an LPG tank. You put in hydrogen, get hydrogen once you have filled in the material.
I guess that's it. We are done with the questions. Thank you very much. Thanks a lot for your presentation.
Thank you.
Thank you, Pratibha ji. This was an excellent presentation, and I'm sure you have made several people interested looking at the number of questions that were put across to you. Thank you very much again.
Thank you, Dr.
We have the next speaker, Dr. Palani Balaya. Dr. Palani Balaya initially worked at Max Planck Institute of Solid State Research in Stuttgart with Professor Joachim Meyer. And after that, he joined the Faculty of Engineering at the National University of Singapore as an assistant professor. And since 2014, he has worked as an associate professor at the same university. His research area includes lithium-ion battery and sodium-ion battery. Today, he's going to speak to us on sodium-ion battery. He served as a topical battery fuel cell capacitor editor for Journal of Solid State Electrochemistry, was elected as an academician by the World Academy of Ceramics of Italy, and elected as a fellow of the American Ceramic Society in 2019. He was recognized as a global ambassador by the same society. He's a recipient of Global Star Award from the same society again. And he is currently in the Intergovernmental Panel on Climate Change as a coordinating lead author for preparing a special report on renewable energy sources and climate change mitigation. Okay, he was in 2011. So we have great pleasure in inviting you, Professor Palani Balaya. Thank you for joining us from Singapore. Over to you now.
Thank you for your kind introduction. Let me start with thanking Lovraj Kumar Memorial Trust for the kind invitation. And as I was introduced, I'm going to focus on sodium-ion battery, but I would like to start with the lithium-ion battery and connect what are the questions we have at the moment as far as lithium-ion battery, and then move on to the sodium-ion battery. In fact, I also want to thank Dr. Ilangovan as well as Dr. Tata Singh Rao. They have already introduced the basics, so it would be very helpful as I move on. As you can see here, these are the 4 chemistries that people use at the moment in the industry. One is a very well known NCA chemistry, NCA, cathode versus graphite. The second one is nickel rich NMC versus graphite, 60-20-20. The third one is cobalt rich NMC versus graphite, 20-20-60. But this is not commonly used. I will explain why this is not commonly used also. Then very well picked up material of LFP versus graphite. So the concerns we have at the moment in all these lithium-ion battery chemistry is safety and supply chain of raw material, which I think both of them talk in detail. So if you look at the various incidences, e-bike in Singapore, the accident has gone pretty large, something like 300% of accidents, somewhere around 2018 to 2019. And even the government banned use of personal mobility device. This is called personal mobility device. And we know that e-scooters and even recently, bus in Hyderabad, during the charging, it got exploded. And this is a big, storage system put up by Tesla in Australia that also got into trouble. And you can see these are 5 buses. Just one bus got fire, and then the set of whole buses here 5, and here somewhere about 20. This had happened in China. This had happened in Stuttgart. So the question naturally, are lithium-ion batteries really safe? This slide was also shared by Dr. Ilangovan. I would like to take this slide. So what is the cause for the thermal runaway? If you have any abuse, it could be thermal abuse or electrical abuse or mechanical abuse. What is happening is you have cathode, you have an anode, you have separator in between, and then electrolyte between all these cathode anode. So what could happen because of these form of abuse? There could be micro inner shock that leads to so-called self-heating. If you allow this to continue, then what happens? Heat accumulates, so-called SEA, solid electrolyte interface, which is formed on the surface of the graphite, because graphite is operating at below 1 volt versus lithium. Lithium is a 0 potential, below 1 volt versus lithium. And anything that operates below 1 volt, you will have reaction between the anode and the electrolyte, forming so-called solid electrolyte interface, which is a polymer layer. This started decomposing because of the heat accumulation. If you still continue, if you still allow it to continue, then separators start melting, and further the anode, which is the graphite, start exposed to air, and then explosion, and then electrolyte explosion, and then rather fire, and then the cathode get exploded, and then you get into so-called thermal runaway. So you should understand what causes the so-called micro inner shorting. I'm going to take 1 or 2 examples and then explain this. This is an example of 18650 cell. So I'm taking 18650 cell, and then I'm going to shake it along the z-axis of the 18650 for 186 days. You can see that the polymer, which is a separator, which is a polymer, it got melted. So that actually shouldn't happen. So this cautions you that whenever you use lithium-ion batteries, you must make sure that there is not much vibration. If you have so-called vibration, that means you are subjecting the cells or pack to so-called mechanical abusement. This is yet another example. I have taken the same 4 chemistry which I have introduced previously: NCA graphite, Gopal-rich NMC versus graphite, nickel-rich NMC versus graphite, Lfp. And then if I look at charge discharge, this is 2-hour charge, 2-hour discharge, or here 2-hour discharge. So 2C discharge means 30 minutes discharge. You can clearly see the Lfp graphite is the one which generates low heat generation. This is actually joule per ampere hour, normalized to ampere hour, because all these chemistry have different ampere hours. So we are normalizing it to per ampere hour. So if you look at Lfp graphite, that is the one which is generating low heat as compared to NCA graphite, then nickel-rich NMC graphite, then cobalt-rich NMC graphite. So that tells you cobalt-rich NMC graphite, this one is not used in industry at all. People discard that, but it has its own interesting physics as well as chemistry, which I will not cover right now. Then if you go to 5C, which is 12 minutes charging and 12 minutes discharging, you can see only Lfp chemistry can be charged and discharged in 12 minutes. None of these oxide chemistries works. That's why the Lfp chemistry is highly robust as compared to the oxide chemistry. And there is another advantage with Lfp chemistry, that is the PO4 bonding, which actually Dr. Kaswara also mentioned. PO4 bonding is extremely strong. By chance your BMS fails, and then you go beyond the cutoff voltage of 4.3 volt for the charging cutoff voltage, then the oxygen is not released. Whereas in all these oxide material, oxygen is released by chance if you exceed this cutoff voltage, which is about 4.3 volt. Now the question is, why so much of heat generation? That is related to so-called reversible heat and irreversible heat. Reversible heat is because you extract lithium and insert lithium. That is so-called entropy changes in the material, which you cannot help. This is chemistry specific. Whereas irreversible heat resistance, heat generation is mainly because of the internal resistance, so-called I square R. R is the internal resistance. That internal resistance is caused because of electrolyte resistance, contact resistance. On the cathode side, you have resistance. On the anode side, you have resistance, etc., etc. And industries are really struggling to minimize this internal resistance as much as possible, so that one can minimize the reversible heat resistance, and thereby one can basically avoid the so-called thermal abusement. So having said this, this one is also a well-known concept. If you take a lithium cobalt oxide versus graphite, when you are charging, what happens is you are removing lithium, and then this is the extraction of the lithium from lithium cobalt oxide. This potential is somewhere about 4 volt versus 0. 0 is the lithium. That is my reference. You can see here the lithium is taken as a reference. So versus 0, this is happening at about 4 volt or so. When you are removing lithium, you are also inserting this lithium into the graphite. Simultaneously, it is happening. So insertion into the graphite happens at 0.2 volt versus 0 volt, which is the lithium. So you can see here the insertion potential is very low, closer to the lithium metal, with lithium metal reference potential. So if you do fast charging, by chance, if you do fast charging, what happens is you are inherently end up with so-called metal deposition on graphite. And this metal deposition happens in the form of dendrite growth. And that dendrite growth, a sharp needle, can pass through the separator, which is about 10 micron, and it can touch the positive electrode, thereby leading to so-called inner microshorting. So you should always avoid fast charging anytime you use graphite cells. The typical charging rate is about 2 hours, but discharging you can do fast. Because in the discharging, you are extracting the lithium from lithium carbon graphite and then inserting into the so-called lithium 0.5 CO2. That can be at any rate. But insertion or the charging should always be done slow rate, typically about 2 hours. Now you may ask, okay, I want to do fast charging. I cannot wait for 2 hours during the charging station. I want to do it in 15 minutes or 20 minutes. Is that a technology? This was also touched upon. This is not something new I'm telling. This was touched upon by Dr. Narsingh Rao, and I'm going to just cover 1 or 2 slides only. The insertion potential and extraction potential in lithium titanate is about 1.5 volt, far away from the 0 potential, which is the lithium reference, whereas a graphite operated 0.2 volt, as I told you. So this is unsafe, whereas this is safe when it comes to quick charging, quick discharging. I can do it in 15 minutes charging. I can discharge it in 15 minutes charging. Incidentally, this material is having 0 strain, so large number of cycles can be covered, and it is extremely safe. You can see here, Toshiba has commercialized that. And then you may ask, what is the problem? Why can't we go ahead with that? The problem is the following. The problem is because the lithium titanate is operating at 1.5 volt and the cathode is operating somewhere about 4 volt. So the typical voltage is in the range 2 to 2.4 volt, and hence the energy density is far less as compared to LFP graphite. LFP graphite in 18650, you can take somewhere about 100 to 105 watt-hour per kg, and the cost is about $100 to $125 per kilowatt-hour. Whereas here, this is about $500 per kilowatt-hour. So any technology you take NMC versus LTO or LFP versus LTO, the cost is pretty high, $500 per kilowatt-hour. It is safe. It helps you quick charging, quick discharging. Unfortunately, it is at least 5 times higher than LFP versus graphite. But you should bear in mind, this is the only technology that is used in marine industry. You look at anything, it is ferry or fishing vessel or yacht, anything, big ship, big vessel, anything you take, only the LTO technology is globally used. None of the graphite technology used, mainly because of the huge vibration that is subjected to the ship or ferry. So you need to bear in mind that anytime you have mechanical vibration, you have to use this type of lithium titanate. However, I told you just now that the lithium titanate technology has lower energy density and it is very expensive. So the question is there an alternate that can give comparable performance as that of lithium titanate, but it is cheaper, somewhere about $100 to $120 or $130 per kilowatt? That is the open question. That's where I'm going to talk about sodium-ion battery. So you know that the lithium chemistry, although it is extensively accepted, you always have so-called supply chain issue, because lithium material, the so-called lithium supply, is typically somewhere in South America or maybe in China or maybe in Australia, but then it leads to so-called geopolitical issue. I don't have to tell this, particularly to the Indian community, they know that very well. The question is there any, a smart way of handling the so-called supply chain? Of course, sodium compound is available in the seawater. So that is one way to go. That's where you don't have to depend on any country. That's the way to go. This is something which I should acknowledge. Faradion in UK have successfully, demonstrated this at least at 1 kilowatt-hour, pack level. And then Reliance in India has bought it 100%. They bought it for 100 million, pounds. So this is a good example. I'm just taking this as a reference. But there are also technologies developed in France and in China, etc., etc. CATL, for example, is a well-known lithium-ion battery manufacturer. They are going to introduce sodium-ion battery by 2023. So in that case, how does our sodium-ion battery technology that is developed in NUS differ from others? We have three components. You can see electrolyte, we use non-flammable electrolyte. We use a robust cathode, which is a phosphate, the PO4 based cathode. And we also use our own in-house carbon. I'm going to show a few examples that will convince you that we are probably moving in the right direction. Let me start with the electrolyte. The electrolyte is non-flammable and it is also thermally more stable. You see here, this is the tetraglyme-based electrolyte, glyme-based electrolyte. And if you bring any fire, it is basically doesn't catch fire even for 60 seconds. Anything does not catch fire beyond 20 seconds, you can categorize them as non-flammable. Whereas the carbonate-based electrolyte, which is widely used globally by any industry that I just now referred, they all catch fire in about 10 seconds to 15 seconds. So flammable electrolyte, first point. Second point is, if you look at this green one, this is the DSC data. You can see here the thermal stability is pretty high, up to about 250 to 270 degrees centigrade. Whereas the red one, which is the carbonate-based electrolyte, it undergoes huge thermal event at about 135 degrees centigrade. This tells me that the glyme-based electrolyte we use non-flammable, and then it is highly thermally stable compared to the rest of the electrolyte. This particular electrolyte, this so-called tetraglyme, has been used in different cathode material. You can see that the performance in hard carbon. Hard carbon is a well-known anode material used for sodium-ion battery technology. You can see here I'm using carbonate-based electrolyte, NaClO4 in EC ethylene carbonate, PC propylene carbonate. The performance is not that impressive. It has a Coulombic efficiency. That means insertion of sodium and extraction of sodium, if you look at the ratio, it is about 70%. And the cycle life is also not so impressive. Under the same testing condition, if I use tetraglyme, I can get about 85% Coulombic efficiency, which is very good. And the cycle life is also pretty good. And recently, there are publications after our work on this tetraglyme and hard carbon. I can cite Shirley Ming from University of California, San Diego. She published very good data on this and analyzed why tetraglyme is working very well with the hard carbon. We also published several papers on that direction. Now, if you look at the sodiated carbon and then desodiated carbon, I'm inserting sodium into hard carbon, and then that sodiated carbon is now subjected to DSC. You can see the thermal event happens somewhere about somewhere here. The first onset is 161 degrees centigrade. This is 161 degrees centigrade. And the energy involved, that is the area under this curve, is about 237 joule per gram in tetraglyme. Whereas if I take carbonate-based electrolyte, you can see the thermal event happens even at much lower temperature, and the energy, the amount of energy released in the sodiated hard carbon using carbonate-based electrolyte is much larger than the glyme-based electrolyte. This tells you that the glyme-based electrolyte is more safe when it is used along with the hard carbon or sodium titanate or any other anode material. And this is a very good example of so-called internal resistance. When you are inserting sodium into hard carbon, you can see here the diameter of the semicircle is much lower than the blue one, which is the sodiated hard carbon using carbonate-based electrolyte, which tells you that the internal resistance associated for the sodiated hard carbon and desodiated hard carbon using tetraglyme is much less as compared to carbonate-based electrolyte. So we have several convincing arguments that tetraglyme is a way to move forward. Here I am moving to hard carbon production in our lab. You can see here this is actually one form of hard carbon. I will not go into the detail. This is BB. You can look at 1400 degrees centigrade is 307 milliampere hour per gram. This is DC, 1400 is 251. And I'm comparing that here with the commercially made. This is type C. This type C is commercially made, which is the pink. You can see compared to the commercially available, which is HECA, we got it from Sri Lanka. Compared to the commercially made, our material is much better performing. In terms of the capacity, in terms of the rate performance, you can see 3C is typically about 20 minutes discharging. 3C, the capacity is far better as compared to the commercially available hard carbon. Most importantly, you must look at this plateau. You look at the plateau and the slopey region. You see here, the plateau is longer and the slopey region is shorter. That's very important. The plateau is the one which is going to give you the difference of the cathode and the anode potential and the actual potential of the full cell. So the plateau has to be longer, and that is something which we are able to achieve with the help of our material, so-called DB 1400 degrees centigrade. And these are rate performance and Coulombic efficiency. So that's the brief information about hard carbon. Let me now move on to the cathode material. We use, as I told you, polyanion, sodium iridium phosphate. You can see here, this is a simple reaction using 5-liter reactor and producing about 0.5 kg sodium iridium phosphate per reaction. So let's not go into the detail now, that they are all already published, but we have a patent on that also. So that is the kilo scale lab we have, 5-liter reactor, which I showed in the previous slide, 20-liter reactor and a 200-liter reactor. This is so-called a retort furnace. That means the furnace under argon atmosphere. You can go typically about 6 kg or 8 kg per batch, depending on the packing density of the material that you are producing. So what we do is, when we go to 200 gram to 3 kilogram, we can convincingly tell you that the structure is not changing except introducing minor impurity. Fortunately, it does not affect the storage performance, as you can see on the right side. This is the extraction of the sodium from sodium iridium phosphate. This is the insertion of the sodium to sodium iridium phosphate against sodium metal. And you can see 200 gram to 3 kilogram, it does not change the performance at all. So why, of course, we are worried about the kilo scale lab? Of course, Dr. Nasingrao also convinced you on that point. But my argument is very simple. If I'm going from 5 gram to 510, I'm actually multiplying it by, let us say, 1,000 times. So sorry, 1 million times. If I can absorb the risk of moving from 5 gram to 5 kilogram, that means I'm taking it up 1,000 times multiplication, then moving from 5 kilogram to 510 is another 1,000 times. That basically shallow the risk which is taken by the investor. Otherwise, there is a deep valley of the risk if somebody is putting $10 million or $20 million to scale it up. This is extremely important. We should shallow down the risk so that investors come forward and then they put in the funding. So we make use of this kilo scale lab to convince the investor. And then we also produce with the help of a prototype line. You can see we have 1% dry room and 20% dry room. We produce commercial type cells. And anytime we talk in terms of the energy density of the full cell, complete weight of the cell. Whether it is a cylindrical cell or pouch cell, we are able to make, but typically about 1 to 3 ampere hour, not more than that. If we need beyond that, we have to work with somebody else. Here I'm giving you a very good example of NVP, hard carbon, non-flammable electrolyte. You can see here I'm charging, that means removing the sodium from sodium iridium phosphate and then inserting it to the hard carbon until here, and then reversing the process. That gives me an energy density of 60 watt-hour per kg. I must confess that this has been now improved to 67 to 68 watt-hour per kg with a certain further modification, but I'm not able to include those data at the moment. So we are somewhere about the 68 to 70 watt-hour per kg. If you go for the soft packing, it is equivalent to about 90 watt-hour per kg. Here I'm showing you the rate performance. Typically, the charging rate is somewhere about C/2, 2 hours, but discharging, I can go by 7 hours, or I can go by about 5C, closer to 5C, 12 minutes. So if I discharge in 12 minutes, I'm still able to retain 83% capacity. That's very important. This is yet another impressive data. 1,000 cycles we are able to do with a 90% DOD, depth of discharge, and retaining about 77% capacity. Please take note that this is our first generation sodium ion cell. So I will skip this oxide material. Actually, basically, we worked on oxide material also, and then we have improved the performance. We have made it water resistant. So you can see here 30 days of water resistance of this particular material, sodium, copper, iron, manganese oxide. And then we have also shown a full cell performance. I'm going to skip because of lack of time. So the message here is our sodium ion cell uses non-flammable electrolyte, and it does not have dendrite growth. That's the most important thing. Dendrite growth, no dendrite growth. We are targeting about 150 to 170 watt-hour per kg in about 2 to 3 years, 3,000 cycles, and charging typically about 15 minutes or so. So we have our own technology for that. And then this is a summary of what I mentioned. I talked about non-flammable electrolyte. I talked about hard carbon. I also talked about sodium iridium phosphate, but in view of lack of time, I could not go into the detail of this, but very detailed paper is there already. So with that, I would like to thank all the group members in my, thanking all of them, and then Ministry of Education, NRF, as well as NUES for the funding, and thank you for your attention.
Thank you very much, Professor Balni. It was a wonderful presentation. I have couple of questions, quick questions. Why not go for an aqueous-based batteries? I mean, like, is it possible to have aqueous-based batteries? Will it, work on, you started talking about, the problems related to lithium. So if we have aqueous-based batteries, will it alleviate?
There was a startup company from Carnegie Mellon, which is called Aquan Energy. They gone into bankruptcy, and then a Chinese company bought it over using aqueous electrolyte. The limitation is that you can't go beyond certain volt, maybe typically about 1.5 volt or 2 volt, not more than that. Here we are able to achieve 3.2 volt. So that's using non-flammable electrolyte.
Another question before we move on to the next person. Will charging and discharging lead to large amount of waste and entropy creation?
That is something which we have to optimize. As I told you, the entropy loss is chemistry specific. So when we are optimizing the chemistry, we need to choose appropriate chemistry so that the entropy loss is minimized. Only there is a irreversible, heat loss, which is due to the internal resistance. And then we play around the several ways of minimizing the internal resistance. I actually don't have time. We have perfect way of looking at what is the cost from the anode and the cathode, giving rise to so-called internal resistance. And since we have prototype line, we can control that particular contribution. Thereby, we bring down irreversible heat loss. The reversible heat loss is something which we cannot touch, but we have to play around the chemistry.
There are a few other simple questions, but I think due to lack of time, probably we'll just move on to the next speaker. Thank you very much, Professor Palanibalia, for a wonderful presentation.
Yeah. Thank you. Thank you.
Thank you very much, Professor Palanibalia. This was an excellent presentation. I know you have not satisfied all the viewers because some of the questions haven't been answered, but we have some lack of time today.
Yeah, that's no problem. At least they have idea, they can reach out to me anytime. Yeah, no problem.
Thank you. Thanks for the offer. We go to the next speaker, Dr. Neil Sirosh. Dr. Sirosh is currently CTO at Gatek Gases in the USA, developing advanced hydrogen and CNG systems in a joint venture with Indian company, Shigan. He was earlier head of hydrogen storage at the Universal Hydrogen, a startup by Airbus and other companies. He was a founding manager at Quantum Technologies, also in USA, a pioneer in hydrogen storage systems. Was with Light Sail Energy, a compressed air energy startup. Served as an advisory council member on alternate energy and was involved in standards being developed on hydrogen, along with CSA, ASME, NFPA, ISO, etc. He holds several patents, has about 40 papers and 3 books to his credits. He is a PhD in finite element from University of Calgary, MBA from University of California, and a graduate in engineering from NIT Trichy. Warm welcome to you, Dr. Neil. Please take over and over to your presentation, please. You'll have to unmute yourself, please.
Yes, sir. Thank you to the organizers, especially Dr. Malhotra for inviting me, and also for the encouragement from Shishir and Gagan Agrawals. Okay, so let me go on to my slides. All right, so you can see it, okay?
Not yet.
Okay, not yet?
Not yet. It only shows started screen sharing, but the slides haven't come out yet.
Okay, still no?
No, not yet. Yes, it's come now. And Dr. Neil, they are visible. You can start now.
You are muted. You just have to unmute yourself, Dr. Neil. Now.
Okay.
Yeah.
Everything okay now?
Everything okay?
All right. All right. So I'm based in Houston. It's early morning. I'm just waking up. And so my presentation is a little bit different from the other eminent speakers this evening because I have no chemical formula. I will not talk about any, I'm not going to talk about lithium or sodium and things like that. It's all about a high pressure hydrogen in a very, very simple storage. In the beginning, we had a very good introduction from Professor Basu. He talked about the renewable energy. He talked about the intermittency. I mean, essentially, it's all about solving this particular formula. In other words, we have very, very clean renewable energy from wind and solar. Unfortunately, it is intermittent. But in order to solve for the intermittency, typically what people do is you rely on the grid. In other words, maybe you have a large solar farm, but when the sun starts producing, you have to rely on the grid to make up the power. But what does the utilities do? They had to fire up these large peaker plants. In other words, you need maybe a natural gas based system that is very polluting in short periods of short bursts. So sometimes it's kind of ironic that in presence of very, very clean renewable energy, we have to rely on this very polluting electric plants, electric generation. So sometimes it's very, very ironic. And the solution to that, of course, is energy storage. But this energy storage needs to be economical and it needs to be scalable in order for this whole thing to work. So in order to enable this sustainable, abundant, renewable energy to become a truly mainstream, we definitely need energy storage. That's the key. So it's very, very timely that that you have this conference today. Now, other speakers have talked about the various options. The energy storage requirements, they differ in their rated power, energy capacity, the discharge time for some, and the energy requirements sometimes is just 1 second, like in capacitors, or 1 minute, or sometimes you need to have in an hourly basis, or sometimes it's many days or a month. So when you are talking about energy storage in the context of renewable energy, you're probably talking in terms of days. So some of the requirements are high energy capacity. One of the initial speakers talked about maybe 70 gigawatt hour today in the world. But essentially we are talking about in the gigawatt hour scale, the energy capacity is definitely not in megawatts or kilowatt hours. We also need a high rated power. Let's say for an industrial complex or a small city, definitely we are going in the 100 megawatt type of range. And the other key is the capacity degradation. Let's say you're a project developer, you need to have this project with a very large renewable energy project, solar or wind, and you want to have this storage system. You want to make sure that it is kind of staying constant for the next 15 years or so. So you can go to the bank and raise finances and so on. But if there is a degradation of, let's say, 20 to 30%, you have to account for that. So that'll have a tremendous strain on the financials for that project. And the other one is portability. Let me explain what that means. Let's say you have a very large, just to give you a practical example, I was living in California for about 20 years. And there's a lot of solar irradiance in California, especially in the deserts towards the east of the coastal cities. But the problem is you can raise a lot of renewable energy, but there is no way to get it into the population centers. In other words, there's no grid. And in order to put the grid, it takes a lot of money. It takes many, many years. So many projects cannot go further because of the lack of the ability to take this stranded renewable energy on to where it is needed. So the portability of the energy also becomes important. That's where one of the advantages of hydrogen comes in. And also you need to have multiple uses. I think that becomes evident with the hydrogen. It can be used for electricity. In other words, You convert electricity to hydrogen, you store hydrogen, and the hydrogen, converting it back to electricity using fuel cells, or it can be used for fuel for mobility or industrial applications. There are many, many industrial applications that are coming up that uses hydrogen. Many speakers talked about energy density. Let me give you a practical example here. This is, let's say, for example, you want a 30 megawatt system and you want to store for 48 hours, which is equating to about 1.44 gigawatt hour energy storage. The amount of batteries, these are the lithium and batteries. If you want to store, if you want to provide this storage, this 1.44 gigawatt hour storage using batteries, the calculation is that you need about 30,000 square meter. These are all industrial buildings, so the space required for the batteries is almost similar to these big industrial buildings. But if you compare that with let's say fuel cells, the fuel cells are right here. This is a real life example. It's about 1/10 of the area that is required for the batteries. But the fuel cell itself is not enough. You also need to have hydrogen storage. For hydrogen storage, you need another 2,000 square meters or so. But the combination of the 2,700 for fuel cell and the 2,000 for the compressed hydrogen storage, it is still very small compared to some of the alternatives. In this particular case, for this 1.44 gigawatt hour, just to give you an example, we can use some compressed gas trailers. I'll show you more details a little bit later. Let's say about 70 of these trailers, they can be stacked too high in order to minimize the footprint that is required. You need about 80,000 kilograms of hydrogen for this, and it can be stored very comfortably. This particular comparison of the cost of energy storage, I actually copied it from one of the presentations from Reliance last year. And the numbers shown here in gigawatts, let's say, for example, the battery storage of 15 days. And if you want only 6-hour energy coming out for 15 days or 24/7, for 15 days at 24 hours, and also hydrogen storage for the same 15 days, 24 hours. So you see the projected costs, these numbers are from Reliance. It's about the hydrogen storage is about 10% of that of batteries. So it looks very attractive. How does what is the other alternative? I mean, currently, if you want power, you go to a diesel generator. And if you compare the overall levelized cost, there is a capital expenditure. There is, like, in terms of the diesel genset, it's about 800. I'm sorry about in dollars, $800,000 per megawatt. If it is a fuel cell generator, it's about $1.5 million per megawatt. There is the fixed overhead, of course, is it's about equal for both the units. And fuel cost, diesel right now in India maybe about 80 rupees per liter, something like that. And hydrogen, I think it's very reasonable to assume about $4 a kilogram. And if you plug in these numbers into the overall cost, in other words, you're actually taking the capital expenditure, the operating expenditure, the ongoing fuel cost, and so on, and the maintenance cost. The cost of energy, in other words, $1 per kilowatt hour, it's almost identical. In other words, this hydrogen and fuel cell is not just a pipe dream, it is cost effective. It is kind of a mature technology now, and it is available right now. So when we look at the entire hydrogen value chain, the focus of this conference is really the renewable energy, the clean renewable energy, and storing that renewable energy in various technologies. So when you have low cost and abundant renewable energy, that can convert to low cost green hydrogen. So when we say green, I'm sure you're familiar with that term. If hydrogen is produced from renewable energy using electrolytes, that's called green energy. But if the hydrogen is produced from, let's say, natural gas, if you're reforming natural gas to produce hydrogen and you're capturing the carbon that is the byproduct, then it's called blue hydrogen. But if it is the traditional steam methane reformation from natural gas, it is gray hydrogen. The majority of the hydrogen that is produced in the world is the gray hydrogen, but definitely there's a pathway towards blue hydrogen. And recently there's a lot of interest in green hydrogen. When we talk about there are of course cost differences between them. The gray hydrogen is typically produced maybe $2, in that range. That is just the production, not including transportation and delivery costs. But if it is green hydrogen, it can go much higher. It can be perhaps $10, maybe $15 a kilogram. That definitely need to come down. But one clear thing that is going on now with the trend towards green hydrogen is that it is being produced in a distributed fashion, in a smaller scale. So again, I live in Texas in the US now. Texas produces almost 1/3 of all the hydrogen in the US. And those are all, 99% of that is this gray hydrogen that is coming out of very, very large scale plants reforming natural gas. Then it is liquefied. So it's liquefied hydrogen, gray hydrogen, and mainly driven by the space industry in the US. So that is the current nature of the things. But when we go towards renewable energy, wind farms and solar farms and so on, which are distributed around the country, the likelihood, then we are, definitely going towards green hydrogen, but we are also going into a smaller scale. Scale is required to liquefy hydrogen. That means it's the future pathway looks towards compressed hydrogen. And there is also now a trend for producing hydrogen from biogas and waste gas to create kind of a net zero carbon hydrogen. And definitely in hydrogen, there's a broad-based use and interested stakeholders. In Texas, that I see that even some of the oil majors, I don't want to name any names, but there's a lot of interest in them as well in hydrogen. In other words, zero carbon energy to go away from the traditional ones. And definitely relatively mature technology, right from reforming the electrolyzers storage. Now, one thing I want to say here is the electrolyzer produces hydrogen, then we are storing hydrogen in these storage units, and it can go in two different pathways. One pathway, of course, is going to the fuel cell and creating electricity, and maybe it's going to go back into the grid, or maybe it's going to some usage areas. But the other attractiveness is the hydrogen can be directly used for fueling vehicles as well. Just want to spend a few seconds on what's going on in the US in terms of the hydrogen economy. As I mentioned before, hydrogen production points will be in the hubs of green, low-cost electricity. But unfortunately, those areas may not be the population centers. So the demand locations may be different from the renewable energy. And this may be true in India as well, where there is, the possibility for the large solar farms maybe is away from the cities, and maybe they're not connected by grid. So there has to be some way to connect the two. Similar to in the US, there's a fragmented supply and demand locations, and the existing infrastructure typically unable to move the large volumes of hydrogen between supply and demand points. And that is one of the keys for very effective energy storage. So behind electricity, transportation and storage is the single largest cost component. In other words, you produce hydrogen, let's say from very, very low cost electricity, but that's not good enough. You need to store and you need to transport, you need to get it to where it is needed, and that need to be done effectively. It can be done by pipelines, it can be done by liquid transportation, compressed transportation. I'll talk about those things. In Texas, there are some hydrogen pipelines already because there are many refineries in this Gulf Coast, and hydrogen is transported through pipelines to those very large consumption centers. Let me explain a little bit on the compressed versus liquid because this debate always goes on. It's a little bit confusing. There are three different charts here. First of all, let me let me talk about the cost of, maybe start with the one in the middle. Two different numbers here. One is California gaseous hydrogen, California liquid hydrogen, and Texas liquid hydrogen. The difference between California and Texas is the cost of electricity. Texas is a lot cheaper. So the blue here is the cost of producing hydrogen by electrolysis. In California is obviously a lot more expensive compared to in Texas. But once the hydrogen is produced, then you have to compress it or liquefy it. If it is compressing, the cost of compression is only 23 cents. So $1.64 per kilogram for hydrogen production. Then for compressing, you are adding another 23 cents. Whereas if it is liquefaction, you're adding $2.86. In other words, liquefaction is more expensive than just the hydrogen production. And why is it so expensive? That's because of the cost of the equipment and the cost of energy. So typically about 30% of the hydrogen energy is gone with the liquefaction. Whereas in terms of, if it is a compressed gas, maybe about 10%, maybe less, depending on the ultimate pressure that is used. So the net effect is the ultimate delivered cost is completely different if it is liquefied versus compressed. And this becomes a major factor if you're considering hydrogen for mobility. You want the lowest cost gas. I mean, the fact remains that hydrogen starts as a gas. If it is electrolyzed or if it is from steam methane reformation, hydrogen starts as a gas. And the end use is a gas. In other words, hydrogen is going not as a liquid, but as a gas into the fuel cell. So do we go by the compressed pathway or by liquid pathway? US definitely started with the liquid because of the very large influence of the space programs. But now we see that with the distributed hydrogen penetration, there's a lot more interest in the compressed form of doing things. Now, how do we store compressed gas? Maybe in this very, very large scale with the wind farms or solar and so on, maybe we can store it underground. So this is one of the concepts that is being developed now at some of the national labs in the US. Pre-stressed concrete, steel chambers underground. And typically the scale is, if you want a megawatt hour of storage, you need a 10-foot in diameter and a 20-foot long tank. But this is still under development, and obviously this is not portable. And the other option is maybe long tubes that are buried in the ground, assuming that you have the right geography and the nature of the soil and rocks and so on. That's one of the options that's being considered as well. And this kind of storage is being considered in the gigawatt scale, gigawatt hour scale. So the topic of my presentation is really none of these. It's composite tanks. The tanks that we can use to store hydrogen on the ground or transport it, because transporting hydrogen is becoming very important, actually more and more now. Let me explain what this graph means. On the x-axis, we have the pressure. So going from, let's say, 1 bar all the way to, let's say, 1,000 bar. On the y-axis, we have the diameter, in other words, the size of the tank, which is very important. We are talking about very large scale storage. That means we need to go larger in size. Now, we all see on the road this kind of trailers that transport gasoline or, let's say, propane, things like that. And those are all pressure vessels. There is some pressure in all those containers. And those are typically very, very low pressure, maybe 1 bar. At those kind of pressures, at very low pressures, metallic tanks are pretty sufficient in order to go to very large diameters. But as you go up in diameter, as you go up in pressure, in the operating pressure, now the pressure, of course, is very important to store hydrogen, as some of the previous speakers have pointed out, the density of hydrogen. It's very attractive from a weight, gravimetric efficiency point of view, but a volumetric efficiency of compressed hydrogen is it's pretty low. So you have to go higher in pressure. But as you start going higher in pressure, the ability of metals to support a larger diameter becomes less and less and less, because it's become impractical in terms of the wall thickness, because you have to account for the stress corrosion, hydrogen embrittlement, things like that. So typically when you look at the standards for ground storage for metal tanks, the safety margin is about 5 to provide the right fatigue life and the corrosion resistance and so on. So when you look at the very high pressure tanks, they're all very inefficient, smaller in diameter. You need a lot of them, so the cost goes up. So that's where the composites come into play. So here, what you're seeing is a composite tank. It's about a meter, more than a meter in diameter, almost about 8 meters long. This is a tank that is being, or it's commercially produced now by KTEC. And it gives some advantage because you're able to increase the capacity and also the pressure. You get both the advantages. And the reason for that is decoupling of the corrosion of hydrogen with the strength requirements. In other words, you have carbon composite on the outside carrying the pressure, and you also have polymer lining that takes care of the corrosivity, the corrosion of hydrogen. The safety is very important, and the compressed cylinders are all around us. I mean, it has been around for a long time, beginning with the steam boilers almost 100 years ago. In fact, probably the world's first pressure vessel code was the ASME, the American Society of Mechanical Engineers. At least that's what I heard. Maybe there's a standard in India before that. I'm not quite sure. Anyway, so the work of this ASME, they kept the pressure vessels pretty safe over the years. But the point I want to make is the American Society of Mechanical Engineers actually published about 10 years ago, the very first code that is related to composites. In other words, it took about 100 years to migrate from steel to composites. And I was one of the members in this drafting committee. So we come a long way, but it is kind of paving the way towards a new generation of pressure vessels that are much bigger, that are very cost effective, that is really tailor-made for storing large amounts of hydrogen in this era of renewable energy. When we talk about pressure vessels, if you dive deep into this, you'll keep hearing terms like type 1, type 2, type 3, and type 4. So what that means is type 1 is the traditional all metal, steel pressure vessels that are very common for industrial gases, oxygen, acetylene, natural gas, carbon dioxide. Type 2 tanks is the first innovation. They've taken the metal tanks. One thing to do with the metal tanks is they're incredibly heavy. So type 2 is metals with a composite hoop wrap. So the weight is reduced almost 20% going from type 1 to type 2. But the cost goes up a little bit because we are putting composites. And type 3 is a metal liner with a full composite overwrap. So the weight is significantly reduced, but the cost is also significantly increased. And the last one is type 4 that has a plastic liner, and the composite is carrying the full load. So the one that we are doing right now is this type 4 for very large scale hydrogen storage. And there are many requirements for these things. The polymer liner need to be good for, let's say, -40, need to be good up until about 82 degrees C or so, which is the operating temperature now standardized for hydrogen. And the carbon fiber cannot be too expensive. We are not using aerospace type. The aerospace type of fiber, typically about $200 a kilogram, but we want to be using something of the order of maybe $20 a kilogram, so this to be cost effective. The advantage of carbon fiber composite is that the carbon fiber strength is about 5 times that of steel, whereas the density is only 20% of that of steel. So the combination of high strength and low density give us a very good advantage. You see some of the tanks being manufactured and assembled into these trailers. So these are 53-foot long trailer that can carry about 1.2 tons of hydrogen. The safety is number one, of course, and there are many regulations that we need to go through for ground storage as well as for transportation. For example, in the US, there are standards such as ASME Section 10 that if it is steel, safety margin of 5, but if it is class 3, which is the composite pressure vessels, is 2.25. So that gives a tremendous cost advantage. And the safety margin for composites is lower because the carbon has a very unique fatigue characteristics. There is not too much drop in the fatigue strength. That means the safety margin can be lower. We have to go through many tests in order to qualify these tanks, including burst tests, fatigue cycles, typically about 15,000 cycles. Creep means you keep it at a very high temperature for almost 3 months and they still need to have good burst strength. Flaw tests, you introduce several cuts on the tank and you still need to go through the fatigue cycles, permeation, penetration. Essentially, I mean, these tanks, you actually have to shoot it with a bullet. And typical bullets will not penetrate these composites, so we have to use an armor-piercing bullet. And it's still, I mean, it cannot burst. That's a requirement. And there are similar requirements from ISO standards. And in India, the PISO is responsible for regulating these. And there are ISO standards that are being used in India as well, with a very, very long list of tests that really make sure that these tanks are as safe as they can be. Validation tests, yeah, this is another summary of these tests. And this kind of tests, they all have been passed. So it's a mature technology, it's a safe technology. When you look at natural gas and hydrogen, there are probably about 3 million tanks from various manufacturers in service all over the world in a vehicular application. So similar technologies are now migrating into large scale hydrogen storage, natural gas storage, and so on. So let me just, this is one of my last slides. Just want to talk about the cost. Talking about the cost of the generation of hydrogen and the cost of hydrogen production is about $2.30, let's say. The cost of compression, storage, and dispensing is about $2.25 if you use steel tanks. And this is for an example of a 2,000 kilogram per day project. In other words, it's using a 5 megawatt electrolyzer. And the storage capacity is 70 megawatt hour. So the net effect is that the delivered cost of hydrogen, the levelized cost is around $4.55 if you use steel tanks. But if you use composite tanks, the cost of storage and dispensing or the transportation goes down significantly. The primary difference is with steel tanks, the capacity of a trailer is only around 200 kilograms, whereas in composite it's about 1,200 kilograms. That means you need a much less number of trailers. So when you consider the transportation cost, the overall operation and maintenance cost and the capex and all those things, it's a lot cheaper to use these large composite tanks. So to summarize, hydrogen storage is an attractive solution for utility scale. When you talk about this megawatt hour type of scale energy storage, it helps to overcome challenges with the interdependency of the renewables. It is mature and safe. Large quantities of hydrogen can be stored and transported as compressed gas in carbon composite pressure vessels. We actually see now a change, a migration from liquid to compressed, because now hydrogen is produced as green hydrogen in a small distributed fashion rather than in very, very large centralized steam methane reformation. And these large diameter carbon composite pressure vessels are most cost effective. So energy storage for the future available today. Thank you. Thank you so much.
Thank you very much, Dr. Sirosh. It was a wonderful presentation. I guess we would defer the question and answer session for this talk in the chat session, since we are about 35 minutes behind schedule. So the questions in the chat box may be looked at, and possibly we'll have a discussion with the audience through the chat box. Thank you very much.
Thank you.
Dr. Deshpande, I think you are muted. Can you please unmute and then?
Thanks a lot. Thanks a lot for reminding me. Thanks to you for handling the most difficult part of the first session, that is the question and answer session. Yes, we have been a little delayed, but we still want to go ahead with the panel discussion. And I request all the panel discussion members to be available. Professor Basu will take over the moderation of the panel discussion from here on onwards. Just before I hand it over to him, I just like to go through the biodata of Dr. Ajit Sapre and Mr. Bharatan, who are the two new joinees for the panel discussion. Dr. Ajit Sapre has more than 40 years of experience in oil and gas, refining, petrochemicals, renewable energy business, and has contributed to innovative technology developments and commercialization. He is a PhD in chemical engineering from the University of Delaware and MBA from Cornell University. He has a strong background in technical management, process catalyst development, reaction engineering, biotechnology, modeling and technical computing, intellectual property management. He has published more than 100 technical papers and more than 50 US patents to his credit. Most welcome, Dr. Ajit Sapre, for joining us in the second successive conclave after the carbon capture that we had last time in November. Mr. Bharatan is the Executive Director R&D from HPCL, Hindustan Petroleum Corporation. He is a postgraduate in chemical engineering, has worked in operations and technical services in HPCL's Vizag and Mumbai refineries for over 24 years, and in the corporate office on margin management and project process. Has varied research interests in all areas of refining and sustainability, development and application of them. He has presented several papers in various technical events and given keynote addresses. One more speaker we have, Professor Anil Verma. Mr. Anil Verma is a professor in Department of Chemical Engineering at IIT Delhi. He started teaching from actually IIT Guwahati in 2005. He was a visiting fellow at the Newcastle University in UK, visiting professor at the Washington University in St. Louis. He is an associate editor of the Indian Chemical Engineer, Taylor and Francis Journal, has been awarded the Amar Daikem Award for Excellence in R&D for candidates below 35 years. He was a member of the Indian National Council of the IICHE and was awarded the Best Paper Award on Fuel Cell and Hydrogen Technology at the International Conference in Kuala Lumpur, Malaysia. So it's over to you, Professor Basu, for taking over the panel discussion now. You have to unmute yourself, sir. Please unmute. Please unmute. No, you're still on mute, Professor Basu. You're still on mute. You're not able to hear you.
Yeah. Okay. Now okay. I'm being allowed. It was not allowing me to. So thank you, Sri Deshpande ji, for giving me this opportunity. And I started with the introduction of this program. Now we have the last phase of this today's program, and we'll keep it brief, short, but of course very important. So I will start with Dr. Ajit Sapre from Reliance, and then I'll go to Dr. Bharatan in HPCL, and then finally come to Professor Anil Verma. So I know in Reliance had a big plan. I've been hearing that Reliance has bought Faradion, who come up with actually sodium-ion battery. That's what we hear. And then Reliance also has a plan anyway. They are coming up with a bunk which will allow the battery swapping technology, which will allow the charging of the e-vehicle, And Reliance, of course, has of course have a plan for renewable energy generation, and obviously once you generate, then there is a storage. So we would like to hear that a refinery company at the core, and we all talked about decarbonization, and we have to do it, we know that, and then how it is going to pan out for all energy companies or for Reliance, who are at the core is a refining company, now diversifying to renewable energy and storage, even catering to services like battery swapping technology and charging station, along with their gas stations, which is a new, I think, venture between Reliance and BP, which is going to come up shortly. And then with the announcement of the government going big way in e-mobility and renewable energy, and then homegrown industry, of course, that has to benchmark or with the international standards. So, Dr. Sapre, please, you may tell us about what is the plan for Reliance and how you are going it, and what is future you see in this.
Yeah, thank you for the kind invitation to this prestigious event. Second time in a row, I'm truly honored. I think, as you explained, that Reliance is doing many activities, and all of them are in public domain. And since this is about long range storage, I'm not going to talk about any of those activities, because all of them are in public domain, and you can read the announcements. So what I'm going to talk about is give a different perspective on perhaps breakthrough ideas on long duration energy storage. And it is not for a few hours, but more likely for a few days, and it is in the scale of gigawatt hours that our previous speaker spoke of, okay? So all the traditional stuff about, we're investing in also all kinds of things, whether it is batteries, fuel cells, electrolyzers, green hydrogen, battery swapping, it's all given. But that is necessary but not sufficient from my perspective, okay? And so I'm going to give you a different perspective. Bill Gates, in his recent book on how to avoid climate disaster, talks about long-range energy storage as at least 7 days, 24/7 or longer, to avoid blackouts and brownouts when we are primarily dependent on intermittent renewable energy, unlike what we have in India today. Okay? So in this context, let me talk about two topics. One is about the hydrogen, and other is about the renewable oil from algae. And I'll explain you why it is so critical. So we have developed an indigenous catalytic gasification technology to make renewable hydrogen from biomass with a cost of less than $1.50 a kilogram, $1.50 kilogram, that covers both the OPEX and the CAPEX recovery. So it is essentially very close to the steam methane reforming, but 100% green hydrogen. Now, if I look at the hydrogen storage and transport, we do have a capability to the composites, the carbon fiber composites, for example, what the previous speaker talked about. But in my mind, the LOHC technology, especially with the heavy aromatics in our refining stream, is equally competitive from a cost perspective. So let's not forget about LOHC as well. Now, I guess if I look at the long duration energy storage, so let me talk about our algae to renewable oil technology. I did talk about the last event, but let me elaborate why it is a battery. At the end of the day, we are talking about converting sun's energy with a storage on demand available energy when required, as electricity, for example. So we really have to compare solar PV with the battery technology for splitting water to make green hydrogen and then reusing electricity, versus if I make a renewable oil and just burn it. So what do I do in algae? I essentially convert CO2, sunlight, in a seawater on a marginal land. So it's 100% renewable oil. And renewable oil is nothing but a stored energy. A battery with very high energy density and very high power density. In the beginning, we did talk about all these capacitors, batteries, this and that. Both the energy density and the power density is 2 orders of magnitude higher than any battery today or the battery that's going to be available in the foreseeable future. And so we have developed and de-risked algae to oil technology at a large facility in Jamnagar. And we are in the process of scaling it up to say 10,000 barrels per day renewable oil. And the cost at 10,000 barrels per day for this oil is only $100 a barrel, including CapEx recovery and OpEx, without any CO2 credit or any government subsidy. So you had to look at the $100 a barrel renewable oil as a stored energy and compare that to hydrogen and batteries. So we can turn this renewable oil into transportation fuel or burn it to make electricity. So let's assume we're going to burn this algal delight renewable oil to make electricity in a typical combined cycle CHP plant with electrical efficiency of only 30%, okay? And then we also load it up with removing all the equipment needed to make it, turn the oil into electricity, make sure you have SOx, NOx, particulate, all kinds of emissions, and load all that capital. So I'm going to compare the solar PV plus battery with a long range storage with this burning algal oil to make electricity. So I'm really comparing photons that I'm converting to oil to electrons to a solar PV with a battery to electrons, okay? So let's assume the world is going to go 100% electricity and absolutely we need a long-term storage. And now I'm going to start comparing when I say long-term storage, let's say 7 days of storage for 24/7, not some 4-hour storage that we have with our solar panels today with a very low penetration of renewable energy, okay? Now if you look at the electricity from burning oil at the efficiency I talked about, and if I look at the PV plus a battery storage at today's cost, it is just not competitive at all. So let's look at what the battery cost will have to be just to set a target for the battery guys to compete with the $100 a barrel renewable oil as an electricity production. The battery will have to be less than $20 a kilowatt hour. You know, today, that is, I've talked about almost a factor of 8 lower than the best batteries available. By the way, we are investing in a lot of battery companies. And obviously, when electrification happens, we do need battery, but let's not confuse battery as a means for a very, very large scale gigawatt hour storage. And if I look at a 15-day energy storage, a battery cost will have to be less than $10 a kilowatt hour. Today, we are close to about $150 a kilowatt hour, maybe approaching 120. Now, I have done the same calculations for solar PV plus electrolyzer producing green hydrogen and storing hydrogen for 7 days to make electricity 24/7 through fuel cell, for example. The target electrolyzer cost will have to be down to $3.50 a kilowatt in terms of CapEx. That is factor of 5 lower than today's electrolyzer cost, okay? So please remember, storing high energy density renewable oil is a lot cheaper than any other storage known today and can store gigawatt hour of energy. Now, the previous speaker, Neil, did took one of my slides to tell you how hydrogen is better than battery, but he conveniently left out the last row I had, where I actually talked about how the renewable oil is even better than battery. Anyway, I mean, I'm not saying hydrogen is not valuable. Hydrogen will be valuable, but let's not forget that renewable oil is also equally valuable. And I have written a detailed scientific paper on this whole subject, and it will get published in a peer-reviewed high-impact journal in the near future. So this has been reviewed by others as well, well-known people, if you will. So certainly, this is another way to look at it. What is the long-term energy storage requirement? And this is the first principle concept that I have actually promoting. And since no Western scientist or a startup company is talking about it, probably it hasn't caught attention, whether in the government of India or other places. You know, with 75 years of independence and ambition for Atmanirbhar Bharat, let's promote Indian inventions. Let's not be just fast follower. Now, I did talk about scaling up algae to oil last time, but as you may remember, algae to make proteins is far more profitable business today to meet the hunger and nutrition needs of India than energy. So we will be scaling up algae to oil, first making food or proteins, and then oil. And in my mind, the government of India could accelerate the development of oil, algal oil that is. At one time I was thinking about we can convert the whole run of Kutch where nothing grows and convert the sun's energy into algal oil. And by the way, you can put solar panels on above algal ponds as well. So you can do both. You can do a solar energy and you can have a storage in the algal oil. So to me, that could be entirely a breakthrough concept and actually help leapfrog India, essentially a new way of looking at how to meet energy needs to continue to grow our economies. 100% from a renewable energy. We are blessed with sun, so make both, make solar energy as well as algal oil, and that will solve many problems.
Thank you.
I hope it was somewhat of a different perspective.
You're sure.
I do know a lot about batteries and fuel cells and hydrogen and storage and other things. I could give you a 45-minute lecture on all of these things, including cost and whatever you need if desired. Okay.
Thank you. Thank you, Dr. Sapre. I mean, obviously, this is an eye-opener for all of us about renewable oil, but we know about it. But we didn't know that it is so cheap compared to other storage devices that we have. I
think the reason simply is because when I say $100 a barrel oil, most of the oil guys get scared because the oil industry, oil can be anywhere from $20 to $150, as you know, right?
Yes.
But the issue is not the oil, because most of the oil we're talking about is a fossil oil. And since India, we do not have any subsidy for a renewable biocrude or for CO2 being consumed, right? As a result, nobody's paying attention.
Right.
I mean, this probably is the most efficient way to store large amounts of energy and use it on demand when you need it. I mean, today we do make electricity by burning oil. It's nothing new.
Yes. Okay. Thank you, Dr. Sapre, and I'll hand over to Professor Sampath. I think we can go to HPC, Dr. Bharatan, and if Professor Sampath would like to add something to it.
I don't think there's anything particular to add. Maybe we can just request Dr. Bharatan to give his comments right now.
Yeah, thank you. Thank you very much, and very good evening to all the fellow panelists and all distinguished guests gathered here. I am seeing we were at one point of time 240 delegates were there in this conference. Right now we are down to 107. So quickly I will complete my perspective of HPCL with what at HPCL Green R&D Center in Bangalore, specifically what we are doing, and as a company, what are our initiatives so far we have taken up. I will again start with hydrogen. For hydrogen, we are the first refinery in India to actually place a purchase order for electrolyzer for 2.6 megawatt. It was done 2 months back, and by this year end, the electrolyzer will be up and running in our Vizag refinery, supplying hydrogen to our hydrotreaters. Whatever smaller capacity is there, this is the largest electrolyzer which has been, actually order has been placed by an Indian refinery. So that is business initiative what you have taken. We have a technology transfer agreement with the BARC. So we are right now scaling up a electrolyzer at our R&D center. These are all at a lower level. Hopefully we will be able to scale it up to higher levels in the coming 2 years. Our HPCL Green R&D Center in Bangalore uses only green hydrogen for more than 2 years now for all running our pilot plants. We have our own PEM-based fuel cell, which is almost 110 kilowatt, and we have a captive solar plant. So round the clock, the hydrogen is supplied to our pilot plants, green hydrogen only, for more than 2 years now. Here there is a small variation between what at industry we use and what in R&D center we use. R&D center will have to buy bottled hydrogen. So what we do here is much cheaper than the bottled hydrogen. So economically also it stands, unlike the other industrial one. Just making up a point here. Apart from this hydrogen, balanced hydrogen plants will be as and when the mandates are coming. Based on that, we will be doing, because as of now, it is not economical to immediately switch over. Now coming to energy storage. At our R&D center, we have recently inaugurated a pilot facility for making pouch cells, which is about 1.5 megawatt hour per annum capacity. We have the dry rooms and all other facilities required to fabricate batteries, advanced cell chemistry batteries. Almost in all the chemistries possible, we are there right now. We hope we will be able to do significantly in sodium ion, which worldwide the research is progressing and we are also able to catch up. Lithium sulfur is another one which we have made some good progress. Hopefully that also will be able to scale up in the coming days to come. Supercapacitor, Dr. Tatharao has fully explained. We were associated with the ARCI for their efforts in supercapacitor with respect to identifying low-cost material from a petroleum refinery, and we will take this up and we are trying to now going for commercial level. We will be trying to do now. Now coming back to the industrial or the company level, HPCL is installing chargers across the retail outlets, mainly across highways outside the cities, also apart from main cities, just to support the requirement for EVs, the range anxiety which is there, because of which the EVs are not moving fast. We are trying to support along with other OMCs by installing chargers in our retail outlets. So this is with respect to the industrial perspective. In the short coming future, for regarding solar energy, we have a modest capacity of almost 150 megawatt across India. We will be scaling it up shortly. From R&D perspective, we do have high temperature heat transfer fluids, which is required for CST. When CST gains importance, this heat transfer fluids will be required, which we have already brought up to commercial level. We do intend to do collaborative project with the ARCA and CGCRI to do SOFC and SOECs also in the immediate future. We have a collaborative project with IIT Madras for vanadium redox flow battery, which there is a prototype already working in our R&D. We will try to optimize it and scale it up in the coming years. So these are few of our initiatives, both from our R&D side and from the company perspective regarding this energy storage and hydrogens. Thank you.
Interesting summary. If I can just ask you about the PEM fuel cell that you're talking about. You said 100 kilowatts, right? Is it something that was indigenously fabricated and is it running continuously?
No, 2 years back, actually 3 years back, we bought a PEM. It is not made by us. It is 110 kilowatt PEM bought out.
Okay. Commercial. Is there any work at all on the indigenous fuel cell development with HPCL?
As I mentioned, on solid oxide fuel cell, we are starting a project with ARCA and CGCRI. Apart from that, on electrolyzers, we are working, but not on fuel cell.
But coming to solid oxide fuel cell, there's a lot of interest on solid oxide ammonia-based fuel cell, which turns out to be better than many other systems. Is there any work or any information available right now indigenously, if there is anything?
Okay. On this, I am not aware. About solid oxide ammonia, probably I am not aware.
Thank you very much.
Okay.
Maybe Professor Verma, we have just heard about redox flow battery work that is going on in HPCL and IIT Madras consortium. We know that you are working on redox flow battery and you have developed a kilowatt range of redox flow battery or more. Can you please tell us the future of redox flow battery in India and as a whole, and then the development that you are doing?
Yeah, thank you very much, Professor Basu. So I'll just give the little bit background before I come to the flow battery, because most of the people may not be knowing about the flow battery. So in recent COP summit, which was held in Glasgow, India has committed very ambitious target that by 2030, 50% of the India's electricity requirement will be fulfilled by the renewable energy. And moreover, also promised that to cut its emission by net zero by 2070, which is quite ambitious as compared to the China, which is saying 2060, and the US and other countries by 2050. So therefore, the success and sustainability of the current ecosystem is primarily dependent on the availability of the technologically and commercially viable renewable energy conversion and storage technology. So briefly, if I tell you, so before telling to the flow battery again, because we are moving very fast towards the EV mobility. Okay, electric mobility is very important and we are moving very fast. So, but what about the infrastructure? How we have to charge the battery? Suppose battery is there in the vehicle, which is the, say, primarily the lithium-ion battery. How to charge it? So presently we are dependent on the electrical grid. So, but if I give you a very small data, suppose we have to run a traditional vehicle, IC based, and we want to go say 500 kilometer, we have to fill up 50 liter of the petrol. Using that, what we have to do, we can fill this petrol in 2 minutes. And always we are talking about how fast we can charge the batteries. Suppose if I correlate it, suppose there is a battery, I want to charge the battery as soon as possible, say comparatively to that, say 2 minutes again. So in that case, if I take a vehicle which is having a 25 kilowatt hour of the energy requirement, and it has to go for 250 kilometers, so that will need 0.75 megawatt of the power, single vehicle. Now you see, if the EV mobility is coming up, a lot of people are charging the battery or the EV vehicle at the same time. What will be the load onto the grid? So therefore, the storage is one of the important things. So briefly, I'll tell about what is the flow battery. So this flow battery system consists of an electrochemical reactor, which has a number of cells in series, along with the positive and the negative electrolyte tanks. So the positive and negative electrolyte initially contains a specific vanadium ion concentration in charge state, and are basically circulated through the electrochemical reactor for generating the electrical energy. Once the stored electrical energy in the electrolyte is utilized, or we can say the electrolyte is discharged, the electrical energy either from the renewable sources preferably should be charged to charge the electrolyte by circulating in the electrochemical reactor. And it is interesting to note that this is a closed loop flow and nothing is going into the environment. And this electrolyte can ideally be used for infinite number of charge discharge cycles. Presently, the state of art says that 20,000 cycle we can go for this flow battery. So in the lab, we have done up to few thousands of the cycle. And the main interesting thing is that this flow battery is flexible for the independent scalability of the power as well as the energy. Okay, so we can tune the size of the electrolyte tank. So I'll just give you an analogy so that everybody can understand. Suppose IC based vehicle is there and which uses the gasoline or the petrol, which gives the energy, is basically contained in that petrol, and the engine gives the power. Basically, it gives the energy to the power. So if you want to have more energy, what you have to do, or you have to go for the longer distance, what you have to do, you have to keep more liquid or more petrol into the tank so that you can go for the longer distance. Okay. So in a similar way, this flow battery works. If you have the more electrolyte, you can run it for the longer time, and nothing is going into the environment. Once the electrolyte is discharged, you can again charge it. Now, what we are doing in our lab, that I can tell you maybe in the next 1 minute only. So we are working on how to reduce the cost of the flow battery, because the flow battery is primarily dependent on the vanadium species. So that vanadium is, people use the VOSO4, and the cost of that VOSO4 is 20,000 rupees per kg. Now we have patented the technology where we can use the vanadium from the V2O5. So once we use the V2O5, the cost is 8,000 rupees per kg. Now you say it is V2O5. That means I am having the two moles of vanadium in 1 mole of V2O5. So cost is again half of that. So typically I can say, as with reference to the 20,000 per kg, the cost will be only the 4,000 rupees per kg per vanadium. Okay, so we have made certain demonstration also in the IIT. We have made charging station so that people can charge their mobile laptops and all those things. At the same time, we have got a funding so that we can demonstrate a 5 kilowatt system for charging the small electric vehicle. So we are working on that. We are halfway. Apart from that, we have also got a National Innovation Challenge Award from the DST recently, and they have funded. So in India, there are only 2 projects which are funded. So we are one of them. At the same time, because just doing in the lab may not be very useful, we have to go out of the lab. So what we have done, we are, apart from the demonstrating this system, we have also incorporated a company which is a startup, and IIT Delhi is supporting that startup. So with that, I'll just give you one example in the next 30 seconds. We are also targeting that these flow batteries can also be used for the telecom sector. Means in the telecom towers, you see, there are typically 5 kilowatt of the power is required, and that 5 kilowatt of the power basically is bet by the diesel generator in case once there is no power. If you see in the city, we don't have the power cut. If you go just beyond the metros, you will see the power cut is from the range of 2 hours to 12 hours. So I have done very basic calculation. If I'm discussing about the 5 kilowatt system, okay, I'm comparing DG and the redox flow battery. So suppose we have to run it for 4 hours per day. That means we are talking about the 20 kilowatt hour of the system, and 5 kilowatt is the power. So if I do the 10-year is the life, suppose I am assuming though the life of the flow battery is very high, but on a safer side, I'm just using the 10 year of the life, and the cost of the diesel is 90 rupees. So if I do it for the entire life, which is around 10 years, suppose if I am using for the DG as well as for the RFP, so the capex of the diesel generator is say 1.5 lakh rupees. There's a one-time investment. But if you see the recurring or the operating expenses, this comes out to be around 20 lakh rupees. Whereas if you see the flow battery, the cost, the capex will be 4,000 rupees, and the operating expenditure will be around 5 lakh rupees if we are charging the battery with the help of the renewable energy. And again, in this case, I have taken very bigger values. The solar, suppose we are taking the power from the solar. In that case, I have taken the 5 rupees per unit. No, but typically it is 2 or 3 rupees per unit. So these are the few of the advances we are doing. So we have filed 6 patents. Out of the 6 patents, that three are national and 3 are international. So we are working on the electrode improvement. We are working on the electrolyte. Now, typically people use the Naphthalene in this battery. So we have come up with a very cheap membrane, which is 1 by 100 times the cost of the Naphthalene. So I am seeing very, very great future for the flow battery, and there are a couple of these startups are coming up in the globe, and they are working fine. So in the India, we are also trying to come up to that level and trying to commercialize this technology. We are in touch with some of the telecom operators, and we have some agreements with them that if we are making that, then we can test it in the telecom tower test bed. Apart from that, we are also in discussion with the various mobility, basically small scale mobility operators, so that we can use our system for the charging the vehicles. Thank you very much.
Thank you, Professor Varma. And we would like to know the cost of electricity, the unit cost of electricity from flow battery when maybe I'm using for charging. So what will be the cost per unit?
Yeah, so if I discuss in terms of the levelized cost of energy, so this levelized cost of energy is typically in the range of 10 to 11 rupees for the flow battery. Now, if I want to compare it with the other technologies, so the lithium ion, it vary from 25 to 30. For the DG, 20 rupees to 25 rupees. Lead acid battery around 20 rupees. So for VRFB, it is around 10 to 11 rupees that we have calculated the LCU.
Okay.
There is a comment in the chat box on the availability of vanadium.
Yeah,
and,
so that is, yes.
And the cost again.
Yes, that is very important thing. And wherever I present about the vanadium redox flow battery, this is very common question. So I'll just give one statement, by that everything will be clear. So lithium, if you see the availability of the lithium and the availability of the vanadium. So vanadium is 6 times more available as compared to the lithium. This much I can tell right now.
Yeah, but in most of these cases, recycling is important as well. I mean, lithium is a lot that's being done right now.
Right,
sir. Anything like that happening for vanadium?
Right. So we have the technology. We have again patented it. We can recover. So the salvage value of this battery is very, very high. So we can recover the vanadium, 99% vanadium we can recover. In fact, we are recovering. We are not throwing any of the vanadium in our lab. So whatever we are doing, we are able to activate it. Suppose if I am running the flow battery for say 200 or 500 cycles. After that, there is a cross contamination. So how to take care of that cross contamination? We have to take it out, and then we have to again recharge it. so that we can again utilize. So that balancing we can also do, and we have the capability, and we have filed the patent for that also.
Can I comment on the vanadium availability?
Yes.
Yeah, please.
Yeah, see, we have a fairly large gasification capacity, and the slag we produce actually concentrates the nickel and vanadium and other metals. And we have developed a very cost-effective technology to extract both nickel and vanadium. And actually, we are scaling it up, working with some of the national labs and ourselves. And we have proven this technology at a fairly large scale. So I think one of these days, we may be able to actually commercialize it and supply the vanadium needed in the Indian market. Because our gasifiers are very, very large. The amount of vanadium we would produce actually would be very large quantities.
Now I'll add one thing here, if I allow. So we have also recovered the vanadium from the spent catalyst which is coming from the sulfuric acid plant. So we have the capability, and we are now writing a patent so that we can have the IPO of that.
Yeah, Professor Sampath, you would like to?
Yeah, I mean, nothing particular. I think we had a fairly good session, even though there was not much mentioned about beyond lithium. I mean, there was some mention about lithium sulfur and sodium ion, of course, which is next to lithium that's coming up. But other than that, there are other chemistries that are also being looked at. And there are also interests in using organic materials in batteries, which give fairly good capacity as well as recyclability and also the rate capability in many cases. I wonder if there is any interest from any of the industrial participants and industrial side on such systems, either from HPCL or from Reliance. I don't know if there is any interest in this area.
So that is you're saying in an organic.
That's right. Yeah. Recyclability. So one can possibly, have one component to start with, and then subsequently go into all organic if possible. So that's a long way to go.
Yeah. Dr. Sapre, we are not able to hear you.
Yeah, you're on mute.
No, I mean, you can send me the information because, see, I was involved quite a bit with SECRI, our national lab. In fact, I was their RC chairman for, Dr. Ilongovan knows me very well from those days. So I think when we looked at all the batteries, I mean, we did look at early on organic batteries you're talking about, but it looked like the very early stage and would take a long effort to do it. And, I guess now where we are in our journey, obviously, both the lithium ion and the sodium ion that we are quite active with, and also we invested in AMRI for a battery energy storage, obviously a large effort in hydrogen. And as I talked to you about the renewable oil, I mean, that's the ultimate storage in my mind, and we will scale that up as we, just a matter of time. But you have to understand, I mean, when the technologies have a volume behind them, and the world is working on all kinds of things about hydrogen and batteries. So as a business, for us, it does make sense to be involved with all those developments to Indianize them and bring the cost down significantly lower. When I gave you some of the targets that we need to compete the batteries with the oil business, if you will, right? And those numbers are far more aggressive than what you will have seen anywhere else. So how do you get on a learning curve, and how do you build a capacity and a scale and apply the knowledge of learning to get the cost down so that you become the best possible producer and supplier in the world? But I think I'm interested. I mean, I know this is something I've not looked at in more than a year. So you can send me the information and I'll look at it.
Sure, I should do that.
I'm the kind of guy who always looks at what is at the bleeding edge. So no worries.
It's not inside, it's always the ground.
Yeah. Is there any comment? So there's a comment that Reliance is working on CCUS. I think last seminar we talked about a lot, and your today's talk is all about CCUS anyway. So I think that's taken care of.
No, I think it was not about CCS. It was about long duration energy storage. I think this whole battery thing you have to put in the context of energy density and a power density relative to others. That's why hydrogen is so much exciting, right? And oil is renewable oil is even more exciting. That's the point I'm trying to make. Don't get me wrong. You do need batteries for, because you don't need a long duration storage for many applications, right? I mean, you do need batteries for converting our two-wheelers, three-wheelers, small cars, things like that. You do need fuel cells and hydrogens for long-haul trucks and heavy-duty. Don't get me wrong. We need all solutions. I just wanted to give you an out-of-the-box understanding of energy storage. There are all kinds of energy storage. Now, why just worried about battery? I mean, people are working on just moving the bricks up and down a 20-story building, right? And we know how to store energy by moving water. I did work on something 30 years ago on storing energy in fluidized bed solids. We know how to store energy in liquids. So there's all kinds of storage energy. So let's not get hung up on batteries and capacitors. They have a role, but I have a feeling once you get to a more than 50% renewable energy and you want to ensure your grid in terms of resiliency and reliability, you need to invest heavily in the grid, greening the grid itself. And once you start talking about gigawatt hour of storage, then what do you have? And that's why I wanted to paint a picture. See, we are so early in our journey for renewable energy. So whatever we're talking about of a solar, batteries, this and that makes money, right? And it's important to get on that learning curve. But if you look 10 years down the road and you say, okay, I don't want brownouts and blackouts, and I want cheap cost of electricity, because the cost of electricity will get dominated by storage. Just think about what's happening to the electricity cost in Germany and California when their renewable energy is more than 50% on the grid. The cost is much higher than what they were used to with just pure renewable energy, right? So you have to think about a gigawatt hour scale. Oil can be, very high density oil can be stored in very small space and can be burned to make electricity. That's the point I'm trying to make. So forget about CCUS, that's an entirely different problem.
Yeah. This is because the question was there, that's why. I mean, there was a question on the chat box, so that is why I brought that up.
Oh, sorry. No, I just want to tell you that I was focusing more on the density, both energy density and a power density.
Yeah. Sure. We understood that. Very nice that you brought that up about green oil or green energy from algae. So, is there any point to be further discussed, Professor Sampath? I think we can as well discuss in the panel all sorts of energy sources. I mean, towards the end, of course, we had a agenda on different storage storage medium. I would say from hydrogen to lithium and sodium batteries and supercapacitors, and then we have followed by that we have 3-4 different other type of storage options. And as Dr. Sapre was mentioning that, I think it is mix of everything is going to stay and going to possibly flower one day. And we will have, right now we have a mix of energies from different type of fossil fuel sources. We will have a mix of energy coming from different type of sources, renewable sources, and storage also is from different type of storage medium and for different type of use. And the longevity of the storage will be obviously will vary with a short-term storage and to a long-term storage that we just discussed today. And with this we close possibly, because now it is about close to Indian time, about 7:40 p.m. I think we close it, and we close today's webinar. Wonderful participation from the big crowd, and as well as all the speakers that joined from different continents. And with this, we come to close of it, and I would request Dr. R.K. Malhotra, former Director General of FIPI, who is also our trustee, and give a concluding remark and vote of thanks. Thank you.
Thank you, Professor Basu. I don't think there is time for any concluding remarks per se. It has been a very interesting session. I must thank you and Deshpande to have put together a very wonderful program. thanks all the speakers, participants. I would like to only thank. I have made 4 or 5 pages of notes, but there is no way, no time perhaps, as somebody said that initially we had about 250 participants. That was the success of this event, but now it has dropped to less than 80 or so. So I don't want to spend more of time, but wonderful session that, but only thing is that we have talked about various, mechanisms of energy storage, but the key lies in affordability and accessibility and availability and safety. So I think these are the kind of issues which we have been deliberating. How much each can provide the, how much material will be, which material will be available, domestically or at affordable price for batteries, different kind of batteries we have discussed. Lithium ion, I have been personally also been having reservations that it not only that it consumes a lot of energy to produce such batteries, but the material is a big issue. We don't have any lithium. So alternative materials, it was glad to see that sodium ion and supercapacitors, flow batteries. So those kind of things have been talked. Hydrogen storage, we know high pressure liquid hydrogen. So very nice of Neil to have presented those metal hydrides. Madam Professor from IIT Bombay presented. So I think this has been a wonderful session. And lastly, Dr. Ajit Sapre, to have put together the renewable oil, $100 seems very attractive at this point of time when the oil prices have gone up substantially. So I fully agree with you if we can, but only thing is how much we can produce, that's the issue. So I think with kind of, you said everything together is required. So maybe we'll need all these kind of things, battery storage as well as, and 24/7 availability for 7 days. You quoted Bill Gates. I think that was wonderful. So thank you very much. Thanks to all the participants, and thanks finally to our chairman of Lovraj Kumar Memorial Trust, who has been encouraging us to put together these kind of sessions. I have no time to actually thank each and every individual who have made wonderful presentations. So thank you very much once again. And we would like to now, already I think we are much behind schedule what we had envisaged to close at 7. It's 42 minutes late. So thank you so much.
Dr. Sir, one last comment I would like to make. I think there was a little concern expressed that we started with 240 people who have logged in, and now we are close to.
Yeah, we started with about 2.
But don't worry. See, our practice has been for the last.
How much?
Then now we started with 240 people who had logged in. And now, of course, we are less than 100.
246 at one point of time.
Yes.
One point of time, I saw 246.
So don't worry, sir. There have been almost 600 registrations, and
no, it happens.
To all these 600 registrations, they get a copy of the video recording of the seminar.
Okay,
so those who have, I think the Lovraj Kumar registrants have become used to this practice. They know even if they don't attend, they will get a video recording. So you can rest assured that the conference.
No, I'm not concerned, Deshpande. Don't get me wrong. I'm not.
The conference will be definitely be watched by many more people.
No, I was only saying that since the number has dropped of participants, I wanted to close early. I didn't want to, go for elaborate concluding remarks of 4 or 5 pages of my notes. Thank you so much.
Sounds like Dr. Malhotra is ready for his dinner. So.
No. If you want, I can continue.
Thank you. Bye-bye.
Thank you. Bye-bye.
Excellent.
Thank you all.
Thanks to all the people who have joined in with their technical presentations to make this a great success. Thank you, Professor Basu, for taking the lead, giving us the idea in the trust meeting that we can have a webinar on this subject, and then getting all the concerned people from all corners of the world to join in and give the presentation. Thanks a lot.
Thank you.
Thank you.
Thank you very much. Thank you, everybody.
Thank you.